Hello there, and welcome to Science for Sleep, where curiosity slows down, questions grow softer, and science is allowed to wander without urgency. This is a place for gentle thinking, for quiet wondering, and for letting the mind drift through ideas without needing to hold on to them too tightly. Tonight, we're going to explore something that lives at the very edge of what science can describe, a place so small that the usual rules begin to lose their grip. We're going to talk about what really happens when space reaches the Planck scale, the smallest meaningful size the universe seems to allow. Now, before we move any further, take a moment to notice where you are. Maybe you're lying in bed, lights dimmed, the day finally loosening its hold. Maybe you're listening through headphones, letting the outside world fade into a low hum. Wherever you are, and however you've arrived here, you're sharing this moment with countless others, all tuned in from different places, different times, different rhythms of night. What time is it where you're listening from right now? Is it late enough that the world feels quieter? Or early enough that the night still feels wide open? If you find this space calming, if these slow journeys through science help your thoughts settle, you're always welcome to like the video or subscribe. It helps this quiet corner reach others who might be looking for the same gentle pause. There's no rush, no pressure, just an open invitation. And now, with nothing else to do and nowhere else to be, we can begin easing our way toward a question that sounds small but turns out to be enormous. When we think about space, we usually imagine something vast. Endless stretches between stars, galaxies drifting apart, distances so large they're measured in years of light. Space feels like the ultimate big thing, the great open backdrop behind everything else. But space also has another side, one that hides in the opposite direction, not outward, but inward. As we zoom in closer and closer, space stops behaving the way we expect. At some point, it stops behaving at all. To understand why, it helps to think about how we normally measure the world. Take a ruler. You can measure a table, a room, a building. If the ruler has millimeter markings, you can get fairly precise. Switch to a microscope, and you can measure things much smaller: cells, bacteria, fine grains of dust. Use more advanced tools and you can probe atoms, then the particles inside atoms. Each time it feels like we're just improving our instruments, sharpening our vision, peeling back layers. For a long time, science assumed that this process could continue forever. No matter how small something was, you could always imagine cutting it in half, and then half again, endlessly. Space itself was thought to be smooth and continuous, like an infinitely stretchable fabric. You could zoom in without limit, and the fabric would still be there, just finer, more detailed, but fundamentally the same. But as physics advanced, cracks began to appear in that picture. The equations that describe gravity, especially Einstein's general relativity, treat space and time as smooth and continuous. They work incredibly well for planets, stars, galaxies, and even black holes. On the other hand, the equations that describe the quantum world, the realm of particles and probabilities, don't assume smoothness at all. They deal in jumps, fluctuations, uncertainties. These two descriptions of reality coexist uneasily, each accurate in its own domain, but deeply incompatible when forced together. The trouble begins when we try to ask what space itself is doing at extremely small scales. Not just small by everyday standards, but unimaginably small. Smaller than atoms, smaller than protons, smaller than anything we can directly observe or measure. As we push our theories into this territory, they start producing answers that don't make sense. Numbers explode to infinity. Predictions contradict each other. The math stops being a guide and starts becoming a warning. This is where the idea of the Planck scale enters the story. Named after the physicist Max Planck, it represents a set of natural units derived from fundamental constants: the speed of light, the gravitational constant, and Planck's constant. Among these units is the Planck length, a distance of about 1.6 times 10 to the minus 35 meters. That's a decimal point followed by 34 zeros and then a 1. To put it into perspective, a proton is about 10 to the minus 15 meters across. The Planck length is 20 orders of magnitude smaller than that. At this scale, something strange happens. Space stops being something we can meaningfully describe as a smooth continuum. Our existing theories no longer apply. If we try to measure distances smaller than the Planck length, the energy required to do so would be so enormous that it would collapse the region into a black hole, hiding the very thing we were trying to observe. In a sense, the universe seems to protect itself from being examined too closely. This isn't just a technical limitation of our tools, it appears to be a fundamental limit built into reality itself. Below the Planck length, the idea of distance may no longer make sense, not because we lack precision, but because the concept itself stops applying. It's as if space has a smallest possible grain, and asking what lies between those grains is like asking what lies between the numbers 0 and 0. At first, this idea feels unsettling. We're used to thinking of space as something passive, something that simply exists and holds everything else. But at the Planck scale, space becomes active, restless, unstable. Quantum fluctuations dominate, energy and geometry intertwine. Space and time themselves begin to lose their separate identities. One way physicists try to picture this is through the idea of quantum foam. At extremely small scales, space may not be smooth at all, but instead a constantly shifting landscape of tiny bubbles, tunnels, and distortions. These fluctuations would be incredibly violent, but also incredibly short-lived, popping in and out of existence faster than any measurement could track. From a distance, all of this chaos averages out, giving us the smooth space we experience, but up close, it's anything but calm. It's important to note that quantum foam is a conceptual model, not a direct observation. We can't see it, and we can't test it directly. But it emerges naturally when we try to apply quantum principles to space-time itself, and that's the core issue here. Quantum mechanics governs the small, general relativity governs the large. At the Planck scale, both should matter equally. Yet we don't have a complete theory that successfully combines them. This is why the Planck scale is often described as the frontier of physics. Not because it's the smallest thing, but because it's the point where our understanding breaks down. It marks the boundary between what our current theories can describe and what lies beyond them. Everything below this scale is, at least for now, theoretical territory. As we approach this boundary, familiar concepts start to behave strangely. Time, for example, may not flow smoothly at the Planck scale. Just as space might be grainy, time might come in tiny increments, or perhaps not exist as a meaningful parameter at all. Some approaches to quantum gravity suggest that time emerges from more fundamental relationships rather than existing on its own. Causality, the idea that causes come before effects, may also begin to blur. At very small scales, quantum events don't always have clear sequences. Things can be correlated without a definite order. When space-time itself fluctuates, defining what came first becomes problematic. The neat chain of cause and effect that structures our everyday experience may not apply. Even the notion of location becomes fuzzy. If space is fluctuating wildly, then pinpointing an exact position loses meaning. Particles may not exist at specific points, but rather as relationships within a constantly shifting framework. This doesn't mean that reality dissolves into chaos at all scales, only that the rules governing it are different from the ones we're used to. What makes all of this particularly intriguing is that these Planck-scale effects aren't just philosophical curiosities. They may play a role in some of the most extreme environments in the universe. Near the centre of black holes, for instance, densities and curvatures approach Planck-scale values. The same may be true at the very beginning of the universe, during the earliest moments after the Big Bang. In those regimes, space and time as we know them may not exist in any familiar form. The universe may have passed through a phase where geometry itself was undefined, where the classical picture of space-time hadn't yet emerged. Understanding what happens at the Planck scale could help us understand how the universe began and what happens when gravity becomes overwhelmingly strong. There's a certain humility built into this realization. Despite centuries of progress, despite equations that can predict eclipses and map the structure of the cosmos, there are still regions of reality that remain inaccessible, not because they're far away, but because they're too close, too small, too fundamental. And yet, this boundary isn't a dead end, it's an invitation. Physicists continue to explore theories that attempt to describe what lies beyond the Planck scale. Loop quantum gravity suggests that space is made of discrete loops, woven together into a kind of network. String theory proposes that the fundamental building blocks of reality are not points, but tiny vibrating strings with extra dimensions curled up beyond our perception. Other approaches imagine space-time emerging from information itself. None of these ideas have been experimentally confirmed, but each offers a different way of thinking about what space might be when it can no longer be divided. Each suggests that the smooth world we experience is an approximation, a large-scale illusion built from something far stranger beneath. As we move forward, it's worth keeping in mind that the Planck scale is not a place you could visit or a size you could point to. It's a limit, a threshold where questions change their meaning. Asking what happens when space reaches the Planck scale is less like asking what's at the bottom of the ocean, and more like asking what happens when you zoom in on a digital image until the pixels no longer resolve into anything familiar. From here, the story doesn't stop. It simply shifts. Once we accept that space may have a smallest meaningful structure, we're led to deeper questions about gravity, about time, about the origin of order, and about whether space-time itself is fundamental or emergent. These questions don't arrive all at once. They unfold gradually, each one opening the door to the next, carrying us further into the quiet, uncertain territory where physics becomes less about answers and more about careful listening. And as those questions begin to gather, the Planck scale remains quietly in the background, not as a final barrier, but as a reminder that even the emptiest parts of the universe may be more intricate than we ever imagined. When we talk about distances in everyday life, we rarely think about whether they have a lower limit. A step across a room, the width of a table, the thickness of a page. Even when we shift into scientific thinking, we're still comfortable dividing distances into smaller and smaller pieces. A meter becomes centimeters, then millimeters, micrometers, nanometers. At no point does common sense suggest that we should stop. There's always an assumption that if we had better tools, finer rulers, sharper probes, we could keep going. For a long time, physics shared that assumption. Space was treated as something continuous, meaning that between any 2 points, no matter how close, there was always another point in between. This idea comes naturally from mathematics. On a number line, there's no smallest distance. Between 0 and 1, there's 1/2. Between 1/2 and 0, there's 1/4. You can keep slicing forever, and the numbers never run out. For centuries, space was assumed to work the same way. Smooth, seamless, infinitely divisible. That picture worked well enough for most purposes. Classical mechanics didn't need to worry about what space looked like at extremely small scales. Even early quantum mechanics, which introduced discreteness in energy levels and particle behavior, still relied on a smooth background of space and time. The equations assumed that particles moved through a continuous stage, even if their actions on that stage were probabilistic. But as theories became more ambitious, and as physicists tried to bring gravity into the quantum picture, that smooth backdrop started to look less secure. The problem wasn't just technical. It wasn't simply that our equations became harder to solve, it was that they began producing answers that didn't fit together. When gravity was treated quantum mechanically, infinities appeared everywhere. Physical quantities blew up to meaningless values. The math stopped describing anything we could interpret as reality. This is usually a sign that a theory is being pushed beyond its domain of validity. Just as Newton's laws break down at very high speeds or very strong gravitational fields, Our current theories appear to break down at very small distances. The question then becomes whether this breakdown is merely a limitation of our models, or whether it reflects something real about the structure of space itself. The idea that there might be a smallest meaningful distance arises from this tension. Not the smallest distance we can measure with current technology, but the smallest distance that can exist in a physical sense. A scale beyond which the concept of distance no longer applies in the way we understand it. This scale is associated with the Planck length, but it's important to separate the number from the idea. The Planck length is not just a tiny ruler mark at the bottom of space. It represents a threshold where the interplay between quantum mechanics and gravity becomes unavoidable. To see why, it helps to think about what it means to measure something. Any measurement requires interaction. To measure a distance, you need some kind of probe. Light is a common choice. You bounce photons off an object and see how long they take to return. The shorter the distance you want to measure, the higher the energy of the photons you need. This is because higher energy light has a shorter wavelength, allowing finer resolution. But energy has mass, thanks to Einstein's equivalence between mass and energy. And mass curves space. As you crank up the energy of your probing light to measure smaller and smaller distances, you concentrate more and more energy into a smaller region of space. Eventually, if you try to probe a distance comparable to the Planck length, the energy density becomes so extreme that the region collapses into a black hole. At that point, the act of measurement destroys the thing you were trying to measure. The black hole hides the region behind an event horizon, making it inaccessible. This isn't a failure of experimental technique. It's a fundamental limit imposed by the laws of physics as we understand them. The universe seems to be telling us that there's a smaller scale at which the notion of distance remains meaningful. Below that scale, asking how far may be like asking what time in a place where time itself doesn't exist. The question stops being well defined. This idea challenges our intuition because we're used to thinking of space as something passive and infinitely detailed. But at the smallest scales, space may be more like matter than we expect. Just as matter is made of atoms, which can't be divided indefinitely without changing their nature, space itself may have a fundamental structure that resists further division. Different theories propose different forms for this structure. Some suggest that space is made of discrete units, like tiny building blocks stitched together. Others propose networks or graphs, where distances arise from relationships rather than continuous extension. In these pictures, the Planck length isn't a literal brick size, but a scale at which the underlying structure becomes apparent. What all of these approaches share is the idea that smooth space is an approximation. At large scales, the discrete or relational nature of space averages out, producing the continuous geometry described by general relativity. This is similar to how a solid object appears smooth to the touch, even though it's made of atoms separated by empty space. You don't feel the gaps because they're too small to matter at your scale. But if space has a smallest meaningful distance, it raises a subtle question. Does that mean space is granular, like sand, or is the situation more abstract than that? The answer, at least for now, is that we don't know. The Planck scale marks a boundary of current understanding, not a fully mapped territory. One important point is that smallest meaningful distance does not necessarily mean smallest possible separation between two objects. It means the smallest scale at which the concept of distance retains physical meaning. Below that, the usual tools of geometry may fail, coordinates may lose their significance. The idea of a point in space may stop being useful. In classical geometry, a point has no size. It's an abstract location. In physics, points are more problematic. Fields evaluated at points often produce infinities. Quantum field theory deals with this by introducing mathematical techniques to manage these infinities, but gravity resists these fixes. When space-time itself becomes dynamical and quantum, points may no longer exist as fundamental entities. This is one reason why some physicists argue that space-time is not fundamental at all. Instead, it may emerge from something deeper, something that doesn't resemble space or time in any familiar way. In such views, distance is not a basic ingredient of reality, but a derived concept that only makes sense when many underlying elements interact in a particular way. If that's the case, then the smallest meaningful distance is not a physical gap between two things, but a limit on how finely reality can be described in spatial terms. Beyond that limit, the language of distance simply isn't the right tool. This perspective helps explain why the Planck length appears in so many theoretical arguments, even though it hasn't been directly observed. It's not just a random scale, it's the point where the constants that govern quantum mechanics, gravity and relativity intersect. Any attempt to describe physics beyond this scale must grapple with all three at once. Another way to think about this is to consider resolution. At large scales, you can resolve fine details. You can distinguish one object from another. As you move to smaller scales, resolution improves, until you reach a point where increasing resolution requires energies that disrupt the system itself. At that point, resolution no longer reveals structure, it destroys it. This suggests that the universe may have a built-in limit to resolution, much like a digital image has a finite number of pixels. Zoom in far enough, and the image stops revealing new detail. You don't see smaller shapes. You see the structure of the pixels themselves, or even noise. The analogy isn't perfect, but it captures the intuition. The smallest meaningful distance is not just small. It's the scale at which the description of space changes character. Importantly, this does not mean that nothing exists below the Planck length. It means that whatever exists there cannot be described using the concept of distance as we understand it. Reality may continue, but our usual spatial language may fail to capture it. This distinction matters because it prevents a common misunderstanding. The Planck length is not a wall that reality hits and stops. It's a signpost indicating that a different description is needed. Just as temperature ceases to be meaningful for a single particle, distance may cease to be meaningful at the most fundamental level. As these ideas settle in, it becomes clear that the smallest meaningful distance is not just a curiosity, it's a clue. It hints that space itself may be an emergent phenomenon, arising from deeper principles that don't involve geometry in the usual sense. When we move through the world, space feels perfectly smooth. You can slide your hand across a table without feeling bumps smaller than the grain of the wood. You can walk across a floor without sensing the microscopic gaps between atoms. Even when we think about space beyond Earth, the vast stretches between planets and stars, it still feels like a continuous expanse, an unbroken stage on which everything happens. This sense of smoothness is so deeply ingrained that it rarely occurs to us to question it. Space feels like the most reliable thing there is, solid in its emptiness, consistent in every direction, always there, holding everything else in place. Physics, for a long time, agreed with that intuition. Classical physics treated space as a smooth, continuous arena. You could assign coordinates to any point. You could draw lines, curves, and surfaces without worrying about gaps or irregularities. Even Einstein's general relativity, which replaced flat space with curved space-time, still relied on smoothness. Space and time could bend, stretch, and warp, but they did so smoothly, like a rubber sheet responding to weight. The mathematics assumed continuity down to arbitrarily small scales. But there is a difference between something being smooth to us and something being smooth in an absolute sense. Many things appear smooth only because we are too large to notice their underlying structure. A beach looks like a continuous surface from a distance, but up close it's a collection of individual grains of sand. A metal rod feels solid, yet it is mostly empty space between atoms. Our senses, and even our everyday instruments, average over enormous numbers of tiny details, giving us a simplified picture that works well at human scales. The same may be true of space itself. The smoothness we experience could be an emergent property, not a fundamental one. At large scales, irregularities are washed out, fluctuations cancel each other, and what remains is an effective geometry that looks continuous, But when we push closer to the smaller scales nature allows, that apparent smoothness may dissolve. One reason to suspect this comes from quantum mechanics. In the quantum world, nothing is perfectly still or sharply defined. Particles fluctuate, fields jitter, even empty space, what physicists call the vacuum, is not truly empty. It seethes with temporary particles popping into and out of existence, borrowing energy for brief moments in accordance with the uncertainty principle. This restless activity is usually negligible at large scales, but it suggests that at very small scales, smoothness may be an illusion. Another reason comes from gravity. In general relativity, gravity is not a force acting within space, but a manifestation of space-time geometry itself. Mass and energy tell space-time how to curve, and space-time tells matter how to move. This elegant picture works beautifully for planets, stars and galaxies, but it treats space-time as a smooth manifold, something that can be curved but not torn, punctured or granular. When quantum effects become significant, that smooth manifold picture becomes harder to maintain. Quantum fluctuations in energy imply fluctuations in curvature. If energy can briefly spike in a tiny region, then space-time curvature should spike as well. At sufficiently small scales, these fluctuations could become so violent that the very idea of a well-defined geometry breaks down. This is where the intuition of smooth space begins to fail. If space-time geometry itself fluctuates wildly, then the notion of a smooth surface no longer applies. Instead of a calm, continuous fabric, space-time at very small scales may resemble something more chaotic, constantly changing from one configuration to another. It's worth emphasizing that this does not mean space becomes rough in a tactile sense. There are no bumps you could feel, no edges you could trip over. The roughness is mathematical and conceptual. It has to do with whether distances, angles, and durations can be defined consistently and simultaneously at arbitrarily small scales. In classical geometry, you can always zoom in. No matter how small a region you consider, you can assign coordinates and define distances. In quantum gravity scenarios, this assumption may fail. The act of zooming in may alter the geometry you're trying to examine. The more precisely you try to localize a region of space, the more uncertain its geometry becomes. This tension shows up clearly when we try to combine quantum mechanics with general relativity. Quantum mechanics insists on uncertainty. You cannot simultaneously know certain pairs of quantities with arbitrary precision. General relativity, on the other hand, treats space-time geometry as something that can, in principle, be specified exactly. When these two frameworks collide, something has to give. One possibility is that space-time itself is subject to quantum uncertainty. Just as a particle does not have a precisely defined position until it is measured, space-time may not have a precisely defined geometry at the smallest scales. Instead, it may exist in a superposition of geometries, constantly fluctuating. If that is the case, then smoothness is not fundamental. It is a large-scale approximation that emerges when fluctuations average out. At small scales, there may be no single geometry to speak of, only probabilities for different configurations. This idea is deeply counterintuitive because we're used to thinking of space as the thing in which everything else happens. It feels more basic than particles or fields. Yet modern physics increasingly suggests that space may be no more fundamental than temperature or pressure. These are useful concepts at large scales, but they break down when applied to individual molecules. Consider temperature. We treat it as a smooth, continuous quantity. A room is 20 degrees Celsius. But temperature does not exist at the level of a single molecule. It emerges from the collective motion of many particles. Below a certain scale, the concept simply doesn't apply. Asking for the temperature of one molecule is not meaningful. The same may be true of spatial smoothness. At large scales, space has a well-defined geometry. Below a certain scale, that geometry may not exist in a meaningful way. Instead, what exists are more fundamental degrees of freedom that only give rise to geometry when considered in large numbers. Different theoretical approaches make this idea more concrete in different ways. Some suggest that space is made up of discrete elements, not unlike atoms, though not located in space themselves. Others suggest that space emerges from networks of relationships, or from patterns of quantum entanglement. In these pictures, smooth space is not built from tiny chunks of space in a straightforward way. It arises from how these underlying elements interact. What unites these ideas is the rejection of perfect smoothness at all scales. Space feels smooth because we are large, because we average over countless microscopic details, and because our experiments probe regimes where smooth approximations work extremely well. But this success should not be mistaken for proof of fundamental smoothness. There is also a practical reason physicists suspect space is not smooth at arbitrarily small scales. When they try to calculate physical quantities using quantum field theory in curved spacetime, infinities appear. These infinities are often associated with treating spacetime as continuous down to zero size. Introducing a smallest meaningful scale can act as a natural regulator, preventing unphysical divergences. This doesn't mean that simply declaring space to be discrete solves all problems. It introduces new challenges of its own, but it suggests that insisting on perfect smoothness may be part of the problem rather than the solution. Another way to approach this question is through measurement. Any measurement of space relies on physical processes. You use particles, waves, clocks, and rulers, all of which are subject to quantum effects. As you try to measure smaller and smaller distances, the energy involved increases, and with it, gravitational effects become important. Eventually, measurement itself disturbs spacetime enough to undermine the concept of a fixed background. At that point, smoothness is not just unobservable, it is undefinable. You cannot meaningfully say that space is smooth if there is no consistent way to assign geometry at that scale. It's also important to recognize that smoothness is tied to predictability. Smooth spaces allow for well-defined trajectories and causal relationships. Rough or fluctuating spaces undermine these notions. If spacetime geometry fluctuates, then the paths of particles become uncertain in new ways. This has implications for causality, locality, and the very structure of physical law. Despite all this, smooth space remains an extraordinarily good approximation for almost everything we do. Engineers don't need to worry about quantum spacetime fluctuations when building bridges. Astronomers don't need to account for them when tracking planets. Even most particle physics experiments can safely ignore them. This is why the idea that space is not fundamentally smooth can feel abstract and disconnected from reality. But abstraction does not mean irrelevance. The breakdown of smoothness at small scales may hold the key to understanding black holes, the early universe, and the unification of forces. It may explain why gravity is so weak compared to other forces, or why space-time has the dimensionality it does. It also forces a shift in perspective. Instead of asking what space is made of in the traditional sense, we are led to ask how space behaves, when it behaves smoothly, and when that behavior changes. Smoothness becomes a conditional property, not an absolute one. As this perspective settles in, the smallest meaningful distance takes on a new role. It is not just a tiny length, it is the scale at which smoothness ceases to be a good description. Beyond that scale, space may still exist in some form, but not as a continuous fabric. This naturally raises further questions. If space is not smooth at the smaller scales, what replaces smooth geometry? How do distances, directions, and durations arise from something that is not itself spatial in the usual sense? And how does this transition happen from a regime where geometry fluctuates to one where it settles into the calm, reliable structure we experience? When physicists talk about boundaries, they don't usually mean walls or edges you could bump into. They mean limits built into the way reality behaves, thresholds where familiar descriptions stop working reliably. The Planck length belongs to this category. It isn't a fence at the edge of space, And it isn't a smallest brick you could ever isolate and hold. It is quieter than that, more subtle. It marks the point where the language we use to describe space begins to lose its footing. To understand why this particular length matters, it helps to remember that physics is not just about discovering what exists, but about discovering which questions make sense to ask. The Planck length emerges not from observation but from consistency. It appears when we try to reconcile the deepest principles we know about the universe and realize that below a certain scale, those principles refuse to cooperate. The number itself is famously small, roughly 1.6 times 10 to the minus 35 meters. Written out, it looks almost absurd, a decimal point followed by an exhausting run of zeros. But focusing on the number alone misses the point. The Planck length is not important because it is tiny. It is important because of how it is constructed. It comes from combining three fundamental constants: the speed of light, which sets the maximum speed at which information can travel, Planck's constant, which governs the graininess of quantum phenomena, and the gravitational constant, which determines the strength of gravity. These constants come from very different parts of physics. One belongs to relativity, one to quantum mechanics, and one to gravity. When they are woven together mathematically, the Planck length appears naturally, without any additional assumptions. That alone is suggestive. It implies that the Planck length is not an arbitrary human invention. It is not chosen for convenience. It arises from the structure of the theories themselves. When quantum mechanics, relativity and gravity are all taken seriously at once, the Planck length shows up whether we like it or not. What this length represents is the scale at which quantum effects of gravity can no longer be ignored. At larger scales, gravity is weak and smooth. Quantum fluctuations in space-time are negligible. At smaller scales, quantum mechanics dominates, but gravity is usually ignored because it is so weak compared to other forces. The Planck length sits at the intersection where neither can be neglected. Above this scale, we can safely treat space-time as a smooth background and apply quantum field theory to particles and forces. Below this scale, gravity becomes strong enough, in a quantum sense, to disrupt that smooth background. The distinction between space-time and the things moving through it begins to blur. This is why the Planck length is often described as the smallest meaningful length rather than the smallest possible length. Meaningful, here, has a specific technical sense. It refers to the ability to define distances in a consistent, observer-independent way. Below the Planck length, attempts to define distance lead to contradictions or undefined behaviour. One way to see this is through thought experiments involving measurement. Suppose you want to measure an extremely small distance. You need a probe with a wavelength comparable to that distance. Shorter wavelength means higher energy. As the energy increases, its gravitational influence increases as well. At some point, the energy required to probe such a small region becomes sufficient to significantly curve space-time. Push this far enough, and the region collapses into a black hole. The very act of measurement creates an event horizon that hides the region from observation. The distance you wanted to measure becomes inaccessible, not because of experimental clumsiness, but because the laws of physics prevent it from being revealed. This argument does not depend on the details of any particular theory of quantum gravity. It relies only on well-established principles. Quantum mechanics tells us that higher precision requires higher energy. General relativity tells us that energy curves space-time. Put together, they imply a limit to spatial resolution. That limit is set by the Planck length. This does not mean that space-time suddenly turns into a solid barrier at that scale. It means that the concept of distance, as something that can be probed, compared, and measured, stops behaving in the way we expect. Below that scale, distance may not be a well-defined property at all. In this sense, the Planck length functions more like a horizon than a wall. Much like the event horizon of a black hole marks a boundary beyond which information cannot escape, the Planck length marks a boundary beyond which spatial description loses operational meaning. It is a boundary of applicability, not of existence. This idea can be unsettling because it challenges the assumption that space is infinitely divisible. For centuries, that assumption went unchallenged. Even when matter turned out to be discrete, space itself was left untouched, smooth and continuous. The Planck length suggests that this last refuge of continuity may not survive, but it's important to be precise about what discreteness would mean here. Saying that there is a smallest meaningful length does not necessarily imply that space is made of tiny blocks arranged like tiles. The underlying structure could be far more abstract. It could involve networks, relationships, or algebraic structures that do not resemble spatial objects at all. In some theoretical approaches, such as loop quantum gravity, areas and volumes take on discrete values. Space is described in terms of quantized geometry, where surfaces have minimum possible areas and regions have minimum possible volumes. The Planck length sets the scale of these quanta, but even in these models, space is not simply chopped into little cubes. The geometry is relational and dynamic. In other approaches, such as string theory, the Planck length emerges as the scale at which strings replace point particles. Below that scale, the notion of a point loses meaning because strings cannot probe distances smaller than their own length. Again, the Planck length does not act as a literal cutoff, but as a signal that a different description is needed. Despite these differences, the role of the Planck length remains consistent. It marks the transition from a regime where space-time can be treated as a smooth manifold to one where that treatment fails. This is why the Planck length is sometimes called nature's quiet boundary. It does not announce itself with dramatic effects at everyday scales. It does not interfere with ordinary physics. It quietly sits far below the reach of current experiments, shaping the consistency of our theories without drawing attention to itself. Its influence is indirect but profound. It tells us that our current descriptions of space are incomplete. It hints that space-time may not be fundamental but emergent. It suggests that at the deepest level, reality may not be spatial in the way we imagine. There is also an important philosophical shift associated with this boundary. In classical thinking, space exists independently of matter and energy. In relativity, space and time respond to matter and energy but still exist as a continuous entity. At the Planck scale, this distinction may collapse. Space may no longer be something that exists independently at all. If space-time is emergent, then the Planck length is not a smallest piece of space, but a scale at which space itself emerges from something else. Below that scale, talking about space may be like talking about waves without water. The description assumes a medium that is no longer present. This perspective also changes how we think about infinity. In mathematics, infinite divisibility is perfectly acceptable. In physics, it often leads to trouble. Infinities in physical predictions usually signal that a theory has been pushed too far. The Planck length acts as a natural regulator, preventing certain infinities from appearing by limiting how far spatial division can go. This does not solve all problems. It does not magically give us a complete theory of quantum gravity, but it provides a clue. It suggests that any successful theory will have to respect this boundary, either explicitly or implicitly. One might ask whether the Planck length could ever be observed directly. The honest answer is that it is extremely unlikely. Probing that scale would require energies far beyond anything we can produce. Even the most powerful particle accelerators fall many orders of magnitude short, and the indirect effects of Planck scale physics are expected to be extremely subtle at accessible energies. But direct observation is not the only way physics advances. Many concepts in physics were accepted long before they could be tested experimentally, because they were necessary for theoretical consistency. The Planck length currently belongs to this category. It is a theoretical necessity, not an empirical measurement. That does not make it arbitrary. It makes it provisional. It tells us something important about the limits of our current framework, even if the full story remains out of reach. As we absorb this idea, it becomes clear that the Planck length is not just a number, but a shift in perspective. It forces us to reconsider what we mean by space, distance, and measurement. It invites us to think of geometry as something that may arise from deeper processes rather than existing as a backdrop. This shift does not require abandoning everything we know. At large scales, the familiar picture of smooth space-time works extraordinarily well. The Planck length does not threaten that success. It simply reminds us that success at one scale does not guarantee validity at all scales. And from here, the natural question becomes not just what the Planck length is, but what happens when we approach it. If space is no longer smooth, if distances lose their meaning, and if geometry fluctuates, what does reality look like in that regime? How do space and time behave when their usual definitions start to dissolve? For most of human history, measurement has felt like a straightforward act. You compare one thing to another, a length against a ruler, a duration against a clock. Even when the tools become more sophisticated, the basic idea remains the same. There is something out there, and we can, at least in principle, determine its properties with as much precision as we are willing to invest effort and technology. Measurement feels like a window we can keep polishing indefinitely, each improvement giving us a clearer view. Modern physics began to challenge that comfort long before the Planck scale entered the conversation. Quantum mechanics introduced limits that were not about technological shortcomings, but about the structure of reality itself. You cannot know a particle's position and momentum with arbitrary precision at the same time. You cannot measure certain properties without disturbing others. At first, this seemed strange but manageable. After all, even with uncertainty, quantum mechanics still allowed precise predictions of probabilities. Measurement became subtler, but it did not lose meaning. As we move toward the smaller scales, however, measurement encounters a more profound problem. It is no longer just that measurements disturb what they measure. It is that the very framework that gives measurement meaning begins to dissolve. The concepts we rely on, distance, duration, location, sequence, stop behaving like stable properties that can be assigned numbers. To understand why, it helps to look closely at what measurement actually involves. Measurement is not passive observation, it is interaction. To measure something, you must exchange energy or information with it. You shine light on an object, you bounce particles off it, you place it in a field and observe the response. Every measurement leaves a trace, and that trace carries energy. At ordinary scales, the energy involved in measurement is negligible compared to the systems being measured. Shining a flashlight on a wall does not meaningfully alter the wall. Timing a falling object does not significantly change its motion. The background assumptions of space and time remain intact, providing a stable stage on which measurements can occur. As measurements become more precise, the energy involved increases. This is not a matter of engineering preference, but of physical necessity. To resolve smaller distances, you need shorter wavelengths. Shorter wavelengths mean higher energies. There is no way around this. It is built into the relationship between wavelength and momentum. At first, this increased energy simply means more disturbance to the measured system. In particle physics experiments, particles recoil, decay, or transform under the influence of the probing energy. But the space-time in which all this occurs remains effectively unchanged. Gravity is so weak at these scales that it can be ignored. That assumption fails as we approach the Planck scale. At these extreme energies, the act of measurement does not merely disturb particles or fields, it disturbs space-time itself. The energy required to probe extremely small distances becomes large enough that its gravitational effects can no longer be neglected. Space-time curvature enters the picture in a direct and unavoidable way. This creates a feedback loop. To measure a smaller region, you concentrate more energy into it. That energy curves space-time more strongly. Stronger curvature alters the geometry of the region you're trying to measure. The geometry you're attempting to define is no longer independent of the measurement process. Push this far enough, and the feedback becomes catastrophic. The region collapses into a black hole, an event horizon forms, enclosing the region and preventing any information from escaping. Measurement does not merely fail to give a clear answer, it actively erases access to the question. This is the point where measurement stops making sense in its usual form, not because we lack clever techniques, but because the conditions required for measurement destroy the framework that measurement relies on. Distance, for example, assumes that you can identify two locations and determine how far apart they are. But if space-time geometry is fluctuating violently, those locations are not well defined. If probing them creates horizons, then the notion of separation becomes inaccessible. Time measurement faces a similar problem. Measuring time requires clocks, and clocks require regular, repeatable processes. At the Planck scale, fluctuations in space-time can disrupt the regularity of any physical process. If time itself is fluctuating, then defining a precise duration becomes problematic. This does not mean that nothing happens at these scales. It means that the language of measurement, as we normally use it, is no longer the right language. Measurement presupposes a stable background against which quantities can be compared. At the Planck scale, that background is no longer stable. One way to appreciate this is to consider the role of reference frames. In classical physics, reference frames are assumed to be well defined. You can choose coordinates, define distances and times, and transform between frames smoothly. In relativity, reference frames become more subtle, but the concept still holds. Even though observers may disagree about measurements, each observer can make consistent measurements within their own frame. At the Planck scale, the notion of a reference frame may itself break down. If space-time geometry is subject to quantum uncertainty, then the coordinate systems we rely on may not exist in a fixed form. The idea of a rigid grid laid over space-time becomes meaningless when the grid itself fluctuates. This suggests that measurement failure at the Planck scale is not a technical glitch. It is a sign that the quantities we are trying to measure are not fundamental. Distance and time may be emergent properties that only make sense when space-time has settled into a stable classical configuration. There is an analogy here with fluid dynamics. Concepts like pressure and velocity are well defined for large volumes of fluid. At the level of individual molecules, those concepts lose meaning. You cannot meaningfully assign a pressure to a single molecule. The measurement fails not because your instruments are crude, but because the concept does not apply. In a similar way, asking for the distance between 2 points at scales below the Planck length may be like asking for the pressure of a single atom. The concept itself no longer maps onto reality in a useful way. This has important implications for how we think about the limits of knowledge. There is a temptation to view limits as temporary obstacles, waiting to be overcome by better technology or deeper insight. In some cases, that is true. Many limits once thought fundamental turned out to be practical. The limit imposed by the Planck scale appears different. It is rooted in the structure of the theories we trust most. It arises not from ignorance, but from consistency. Trying to bypass it leads to contradictions, not just experimental difficulty. That does not mean physics gives up. It means physics changes its questions. Instead of asking for ever finer measurements of space and time, it asks what underlying processes give rise to space and time at larger scales. Measurement shifts from geometry to relationships, from locations to correlations. In some theoretical frameworks, the fundamental quantities are not distances or durations, but abstract variables that encode how different parts of a system influence one another. Space and time emerge as effective descriptions when those variables are organized in certain ways. From this perspective, measurement at the deepest level may not involve rulers and clocks at all. It may involve counting interactions, tracking changes in information, or identifying patterns of correlation. These are not measurements of space and time directly, but measurements of whatever gives rise to them. This reframing helps resolve a common confusion. When physicists say that measurement stops making sense at the Planck scale, they do not mean that reality becomes unknowable or meaningless. They mean that our current measurement concepts no longer apply. New concepts are needed. ones that do not assume a smooth space-time backdrop. It is also important to distinguish between operational meaning and existence. A quantity can exist in some sense even if it cannot be measured in the usual way. Quantum states, for example, exist even though certain aspects cannot be directly observed. What changes is how we talk about them and what questions we consider meaningful. The Planck scale may represent a similar shift for space-time itself. Space and time may exist in some deeper form, but not in a way that supports direct measurement of distances and durations. This perspective also sheds light on why Planck scale physics is so difficult to test experimentally. If measurement in the traditional sense breaks down, then experimental access becomes indirect at best. We must look for subtle imprints of Planck scale physics on large-scale phenomena rather than trying to probe it directly. Cosmology offers one possible avenue. The early universe may have passed through a Planck scale regime, and traces of that era could be imprinted in the structure of cosmic radiation or the distribution of galaxies. Black holes offer another possibility, as regions where gravity and quantum effects intersect. Even so, interpreting such signals requires caution. The further we move from direct measurement, the more we rely on theoretical inference. This does not make the endeavour unscientific, but it does demand humility. There is also a psychological aspect to this boundary. Humans are accustomed to thinking that with enough effort, everything can be measured, quantified, and pinned down. The idea that there are aspects of reality where measurement itself loses meaning can feel unsettling. It challenges a deeply held intuition about knowledge and control. Yet physics has encountered such challenges before. The abandonment of absolute simultaneity and relativity, the acceptance of probabilistic outcomes in quantum mechanics, each required a shift in how we think about measurement and reality. In each case, the shift led not to confusion, but to deeper understanding. The Planck scale may represent the next such shift. It asks us to reconsider what measurement is for and what it presupposes. It suggests that measurement is not a universal operation, but a context-dependent one, meaningful only within certain regimes. As we sit with this idea, it becomes clear that the breakdown of measurement is not an endpoint. It is a signpost. It tells us where our current conceptual tools reach their limits and where new ones are needed. In everyday experience, space and time feel like separate things. Space is where events happen. Time is when they happen. You can point to a place without mentioning a moment, and you can refer to a moment without specifying a location. This separation feels so natural that it rarely draws attention. Even our language reinforces it. We ask where something is, and we ask when it happened, as if these are fundamentally different kinds of questions. Classical physics was built on this intuition. Space existed as a three-dimensional stage, fixed and unmoving. Time flowed uniformly, the same everywhere, ticking forward independently of what happened in space. Events unfolded within this framework, but the framework itself remained untouched. You could imagine removing all matter from the universe, and space and time would still be there, empty but intact. Einstein disrupted this picture, but he did not erase the distinction entirely. In relativity, space and time are woven together into space-time, a four-dimensional structure. Space can no longer be fully described without time, and time cannot be fully described without space. Measurements of distance and duration depend on motion and gravity. Observers disagree about lengths and time intervals. Yet even in this unified picture, space-time is still treated as a smooth entity, something that exists and can be described geometrically. As we move closer to the Planck scale, that remaining stability begins to erode. The distinction between space and time becomes harder to maintain, not because they merge poetically or symbolically, but because the assumptions that allow us to define them separately stop working. To see why, it helps to consider how space and time are defined operationally. Space is defined through distance measurements. Time is defined through clocks and sequences of events. Both rely on regularity and repeatability. A ruler assumes stable geometry. A clock assumes a consistent flow of time. These assumptions are reasonable at large scales. They become questionable at very small ones. At the Planck scale, space-time geometry itself is subject to quantum uncertainty. This means that distances fluctuate and durations fluctuate. If the geometry of space is uncertain, then the separation between two events is uncertain. If the geometry of time is uncertain, then the order and duration of events become uncertain as well. In such a regime, it no longer makes sense to talk about space without time or time without space. They are entangled not just mathematically but physically. Fluctuations in one imply fluctuations in the other. This is not merely a technical detail, it alters the conceptual foundation of physics. In classical thinking, you could imagine freezing time and examining space, or holding space fixed and watching time flow. At the Planck scale, neither operation is well defined. There is no stable space to freeze and no uniform time to watch. One reason for this blurring lies in how gravity treats space and time. In general relativity, gravity is not a force that acts in space over time. It is the curvature of space-time itself. Mass and energy affect both spatial distances and temporal rates. Clocks tick more slowly in strong gravitational fields. Lengths are distorted as well. At ordinary scales, these effects are small and predictable. At extreme scales, especially where quantum fluctuations in energy become significant, these distortions become unpredictable. If energy fluctuates, then space-time curvature fluctuates. If curvature fluctuates, then both space and time fluctuate together. This joint fluctuation undermines the separation between spatial and temporal measurements. You cannot say with confidence how far apart 2 points are without also specifying how time behaves between them, and you cannot define a time interval without accounting for spatial geometry. Another way to approach this is through the concept of simultaneity. In relativity, simultaneity is relative. Different observers disagree about whether two events happen at the same time. This already hints that time is not an absolute background. At the Planck scale, the situation becomes more extreme. If space-time geometry fluctuates, then even a single observer may not be able to define a consistent notion of simultaneity across very small regions. Events may not have a definite temporal order. The idea that one thing happens before another may only apply approximately when space-time behaves classically. At very small scales, the notion of before and after may lose its sharpness. This does not mean that causality disappears entirely. It means that causality may not be encoded in time ordering in the way we expect. Instead, causal relationships may be defined through correlations or constraints that do not rely on a fixed temporal sequence. Some approaches to quantum gravity suggest exactly this. They propose that fundamental processes are not ordered in time, but related through algebraic or informational structures. Time emerges as a useful parameter only when many such processes are considered together, producing an effective order. In these views, time is not something that flows at the deepest level. It is something that appears when systems become complex enough. Space and time emerge together, not as independent entities, but as aspects of a larger structure. This idea is challenging because it contradicts our lived experience. We feel time passing, we feel space extending around us, but feeling is not the same as fundamentality. Many things feel basic that turn out to be emergent. Solidity feels fundamental, yet it emerges from electromagnetic interactions and quantum exclusion. Temperature feels fundamental, yet it emerges from statistical behavior. The blurring of space and time at the Planck scale suggests that our experience is built on a stable regime that does not extend all the way down. Below a certain scale, the building blocks of reality may not resemble space and time at all. This has implications for how we think about the beginning of the universe. If space-time itself emerges, then asking what happened before the Big Bang may be a malformed question. Before implies time. If time did not yet exist in a meaningful sense, then before is not applicable. Similarly, inside black holes, where curvature becomes extreme, space-time may enter a regime where the usual distinction between space and time breaks down. In classical general relativity, time and space swap roles inside the event horizon. At the Planck scale, this swapping may be replaced by something even less familiar. Another clue comes from how quantum mechanics treats time. In standard quantum mechanics, time is not an operator like position or momentum. It is a parameter. It sits outside the system, ticking away independently. This treatment works well for laboratory experiments, but it becomes problematic when the entire universe is the system. If there is no external clock for the universe, then time cannot be a background parameter. It must be defined internally, in terms of relationships between parts of the system. This relational view of time naturally ties it to space and matter. Time becomes a way of describing change, not a container in which change happens. When space is also treated relationally, the distinction between space and time becomes even thinner. Both become ways of organizing relationships. Spatial relationships describe how things are arranged. Temporal relationships describe how things change relative to one another. At the deepest level, these may be different aspects of the same underlying structure. This is why many modern approaches to fundamental physics do not start with space-time at all. They start with abstract entities, states, or networks, and ask how space-time might emerge from them. In such frameworks, space and time are secondary, effective descriptions that apply only when certain conditions are met. From this perspective, the Planck scale is not just a small scale. It is the scale at which the emergent description breaks down. Below it, the concepts of space and time lose their independence and begin to merge into something more primitive. This merging does not imply harmony or simplicity. It implies complexity. The underlying structure may be more complicated than space-time, not less. Space and time may be simplifying concepts that hide deeper intricacies. There is also a practical reason why this blurring matters. Physical laws are formulated in terms of space and time. If those concepts break down, the laws themselves must be reformulated. Differential equations that assume smoothness and continuity may no longer apply. New mathematical tools are needed. This is one of the reasons quantum gravity is such a difficult problem. It is not just about quantizing gravity. It is about rethinking the role of space and time in physical law. It requires letting go of the assumption that they are always available as a backdrop. Despite this, it is important to remember that the blurring of space and time is not something we experience directly. It does not affect daily life. It does not disrupt ordinary physics. The emergent space-time we inhabit is remarkably stable. This stability itself is something to be explained. If space and time are emergent, why do they emerge so reliably? Why does space-time behave classically over such a wide range of scales? What mechanisms suppress quantum fluctuations in geometry at larger scales? These questions are active areas of research. They suggest that there may be processes that smooth out space-time as systems grow larger, much like decoherence smooths out quantum behavior in macroscopic objects. The classical world may emerge from the quantum one through averaging and interaction with the environment. As this picture develops, the blurring of space and time at the Planck scale becomes less mysterious. It becomes a natural consequence of emergence. Just as individual water molecules do not have waves, but collections of them do, individual fundamental processes may not have space and time, but collections of them do. This does not diminish the importance of space and time in our lives. It places them in context. It shows that they are reliable features of a particular regime, not universal absolutes. Einstein's picture of space-time is one of the most successful ideas ever developed in physics. It reshaped how we understand gravity, motion, and the structure of the universe. Instead of imagining gravity as a force pulling objects through space, general relativity describes it as the geometry of space-time itself. Massive objects curve space-time, and other objects follow those curves. The image is often simplified as a stretched fabric, bending under the weight of stars and planets, guiding the paths of everything that moves across it. This idea works extraordinarily well. It explains the orbit of Mercury more accurately than Newton ever could. It predicts the bending of light around massive objects. It accounts for gravitational time dilation, where clocks tick at different rates depending on gravity. It even predicted black holes and gravitational waves long before we had any observational evidence for them. For over a century, every serious test of general relativity has confirmed its predictions. Because of this success, it can feel almost ungrateful to talk about limits. But in physics, limits are not failures, they are clues. Every theory that has ever advanced our understanding has also revealed where it stops being reliable. Newton's laws still work beautifully for everyday motion, but they break down at high speeds and strong gravity. Classical electromagnetism works well until quantum effects dominate. In the same way, Einstein's spacetime fabric has a domain where it shines, and a boundary where it begins to fray. The key assumption underlying general relativity is that spacetime is smooth, not flat, but smooth. Curvature can change from place to place, but it changes continuously. You can zoom in as much as you like, and the geometry remains well defined. Distances, angles, and time intervals can always be specified, at least in principle. This assumption is deeply embedded in the mathematics of the theory. General relativity uses differential geometry, a mathematical framework that relies on smoothness. Curvature is defined by derivatives. Equations describe how geometry changes infinitesimally from point to point. If space-time were not smooth, these tools would stop working. At large scales, smoothness is an excellent approximation. Even near massive objects like stars and black holes, space-time curvature varies gradually over distances far larger than the Planck length. In these regimes, general relativity provides accurate, reliable predictions. Problems arise when we push the theory into regimes where quantum effects cannot be ignored. General relativity treats space-time as a classical object. It does not fluctuate. It does not exist in superposition. It responds deterministically to energy and momentum. Quantum mechanics, on the other hand, insist that everything fluctuates. Fields fluctuate, energies fluctuate, even empty space fluctuates. When we try to apply general relativity at extremely small scales, these two worldviews collide. If energy fluctuates, space-time curvature should fluctuate as well. But general relativity has no built-in mechanism for handling such fluctuations. It assumes a well-defined geometry at every point. This mismatch shows up mathematically as infinities. When physicists try to quantize gravity using the same techniques that work for other forces, the calculations blow up. Physical quantities diverge. Predictions lose meaning. These infinities are not just annoying artifacts. They indicate that the theory is being applied outside its range of validity. One might hope that these problems could be fixed by clever mathematical tricks, but decades of effort suggest otherwise. Gravity resists straightforward quantization. The smooth space-time fabric that works so well at large scales becomes a liability at small ones. Another way to see the limits of Einstein's picture is to consider singularities. In general relativity, singularities are points or regions where curvature becomes infinite. The equations predict their own breakdown. The most famous examples are the centers of black holes and the initial state of the universe in the Big Bang model. At a singularity, space-time curvature becomes infinite, and the theory can no longer make meaningful predictions. Distances shrink to zero. Time intervals lose meaning. These are not places where the universe ends. They are places where the theory stops working. Physicists generally interpret singularities as signs that general relativity is incomplete. They suggest that new physics must take over before infinities are reached. The Planck scale is often seen as the threshold where this transition should occur. In this sense, the limits of Einstein's space-time fabric are not arbitrary. They are woven into the theory itself. General relativity predicts its own failure when pushed too far. It does not pretend to describe reality at all scales. There is also a conceptual tension between general relativity and quantum mechanics that goes beyond technical issues. In general relativity, space-time is dynamic. It responds to matter and energy. In quantum mechanics, space-time is usually treated as a fixed background. Quantum fields evolve in time, but time itself does not evolve. This asymmetry becomes problematic when we try to describe situations where space-time itself should be quantum. If space-time can fluctuate, then treating it as a fixed stage is no longer appropriate. Yet quantum mechanics, as traditionally formulated, relies on that stage. Attempts to merge the two frameworks force us to reconsider the role of space-time altogether. Is space-time a fundamental entity, or is it an effective description that emerges from something deeper? General relativity assumes the former. Quantum gravity research increasingly suggests the latter. The fabric metaphor itself begins to show its limits here. A fabric implies something continuous, something that can bend and stretch but remains intact. At the Planck scale, space-time may not resemble a fabric at all. It may not be something you can stretch or curve in the usual sense. This does not mean Einstein's insight was wrong. It means it was incomplete. General relativity captures how space-time behaves when it can be treated as a smooth classical object. It does not capture how space-time behaves when its own quantum nature becomes important. Another limitation appears when we consider the role of measurement and observers. In general relativity, space-time geometry is defined independently of observation. Observers measure distances and times, but the geometry itself exists whether or not anyone measures it. Quantum mechanics complicates this picture. Measurement plays a fundamental role. The act of measurement affects the system. Outcomes are probabilistic. When space-time itself is subject to quantum effects, the idea of an observer-independent geometry becomes questionable. If space-time geometry depends on quantum states, then different observers may not only measure different values, but may not even agree on what geometry exists. This challenges the classical notion of an objective space-time fabric. Some approaches to quantum gravity address this by abandoning the idea of space-time as a fundamental entity altogether. Instead, they describe fundamental processes without reference to space or time, and show how space-time emerges in appropriate limits. From this perspective, Einstein's space-time fabric is like a thermodynamic description. It works when many underlying degrees of freedom act together. It fails when those degrees of freedom cannot be ignored. There is an instructive analogy with elasticity. At large scales, a rubber sheet behaves smoothly. You can describe its deformation with continuous equations. At very small scales, the sheet is made of molecules. The smooth description breaks down. Elasticity theory does not apply to individual molecules. General relativity may be similar. It is an effective theory of space-time elasticity. It describes how space-time responds to energy and momentum when treated as a continuous medium. At small scales, the underlying structure becomes relevant, and the effective theory fails. This view helps reconcile the extraordinary success of general relativity with its apparent limitations. The theory is not wrong. It is simply not fundamental. It is a powerful approximation that emerges from deeper physics. Recognizing this does not diminish Einstein's achievement. On the contrary, it highlights how far his ideas reach. General relativity may be the large-scale limit of a more complete theory, just as classical mechanics is the large-scale limit of quantum mechanics. As we approach the Planck scale, the fabric metaphor gives way to something more restless. Space-time may fluctuate, fragment, or dissolve into relationships that do not resemble geometry. Curvature may no longer be a smooth function. The very notion of a point in space-time may lose meaning. This realization forces change in how we think about gravity. Gravity may not simply be geometry. Geometry itself may be an emergent manifestation of more fundamental interactions. The limits of Einstein's space-time fabric mark the boundary where geometry ceases to be the primary language of physics. When the smooth picture of space-time begins to fail, physicists are left with a difficult task. They still need language to talk about what replaces it. Even though no direct observations are available, and familiar concepts no longer apply cleanly. One of the earliest and most enduring attempts to describe this regime is known as quantum foam. It is not a formal theory, not a precise model with equations that can be tested, but a way of capturing an idea that emerges when quantum mechanics and gravity are both taken seriously at very small scales. The phrase was introduced by John Wheeler, who was deeply involved in thinking about gravity, quantum mechanics, and the structure of space-time. He imagined that at extremely small scales, space-time would not sit quietly in a smooth geometric configuration. Instead, it would fluctuate violently, constantly changing shape, topology, and connectivity. The word foam was chosen carefully. Foam is not solid, not liquid, not gas, but something restless and unstable, full of bubbles forming and collapsing, never settling into a fixed arrangement. This image is meant to convey a loss of calmness. At large scales, space-time behaves predictably. Curvature changes smoothly. Distances and durations can be defined. At the Planck scale, that calm disappears. Quantum uncertainty applies not just to particles moving through space-time, but to space-time itself. To see why such restlessness might arise, it helps to recall what quantum mechanics says about energy. Even in a vacuum, energy is not zero. Fields fluctuate, virtual particles appear and disappear. These fluctuations are usually small and average out over larger scales, but gravity couples to energy directly. Any fluctuation in energy implies a fluctuation in space-time curvature. At ordinary scales, the gravitational effect of vacuum fluctuations is negligible. At extremely small scales, the situation changes. When the region of interest shrinks, the relative impact of fluctuations grows. Near the Planck length, these fluctuations are no longer small perturbations. They dominate. In this regime, space-time geometry may fluctuate so strongly that the notion of a fixed background becomes meaningless. Distances expand and contract. Connections form and break. The topology of space itself may change, with tiny tunnels or handles appearing briefly before vanishing again. These speculative features are often mentioned together. Tiny wormholes, short-lived black holes, rapidly changing curvature. None of these are predicted with confidence. They are suggested by extrapolating known principles into a regime where those principles are no longer fully trustworthy. The important point is not the specific imagery, but the idea that space-time at these scales is fundamentally unstable. This instability is not something that would be noticed by objects much larger than the Planck length. Just as waves on the surface of water are invisible to a boat miles away, Planck scale fluctuations average out at larger scales. The space-time we experience appears smooth because we are insensitive to the jitter beneath it. The term jittering reality captures this well. The jitter is not motion through space. It is the restless rearrangement of space itself. Locations do not simply shift. They may cease to exist as identifiable points. What replaces them are fluctuating relationships, momentary configurations that cannot be pinned down long enough to be measured. One way to think about this is to consider how geometry is defined. Geometry relies on stable relationships. A distance is meaningful only if it persists long enough to be compared. An angle is meaningful only if the underlying structure does not change during the measurement. In a quantum foam regime, these assumptions fail. The structure changes too quickly and too unpredictably. This does not mean that reality becomes random in an absolute sense. Quantum mechanics is not random chaos. It is governed by probabilities and constraints. But it does mean that classical notions of geometry are no longer the right tools. An important feature of quantum foam is that it challenges the idea of locality. In classical physics, events influence one another through nearby interactions. Space provides a notion of nearness. At very small scales, if space-time connectivity itself fluctuates, nearness may not be well defined. Two regions that are far apart in an average sense might briefly become connected through a Planck scale tunnel. Two nearby regions might temporarily disconnect. These effects would be fleeting and statistically suppressed at larger scales, but they suggest that space-time connectivity is not fixed. This idea is unsettling because locality underpins much of physics. Cause and effect are tied to spatial relationships. If those relationships fluctuate, then causality itself may require reformulation, not abandonment, but reinterpretation. Another aspect of restless space is the role of time. In the quantum foam picture, time is not a smooth parameter ticking away uniformly. Temporal ordering may fluctuate along with spatial relationships. The separation between events in time may not be well defined at the smallest scales. This does not imply time travel or paradoxes in the familiar sense. It implies that the fine-grained ordering of events may not exist. Only coarse-grained, averaged order emerges when many fluctuations are considered together. The idea of emergence is crucial here. Quantum foam is not meant to describe what we see directly. It is meant to describe the underlying behavior that gives rise to smooth space-time when averaged. Just as thermal motion gives rise to temperature, Planck scale fluctuations may give rise to classical geometry. In this view, smooth space-time is a collective phenomenon. It is the result of many underlying degrees of freedom acting together in a stable pattern. Quantum foam represents the individual degrees of freedom before they organize into that pattern. This perspective aligns with a broader trend in physics. Many quantities once thought fundamental have turned out to be emergent. Pressure, temperature, solidity, even electric fields in certain contexts all arise from deeper interactions. Space-time may belong to this category. If space-time is emergent, then its restlessness at small scales is not a flaw. It is a feature. It is what allows space-time to have flexibility, to respond to energy and matter, to support dynamics at larger scales. It is important to emphasize that quantum foam is not a complete theory. It is a heuristic picture. Different approaches to quantum gravity realize the idea of restless space-time in different ways. Some replace foam with discrete networks. Others replace geometry with information. Others suggest that space-time arises from entanglement patterns. Despite these differences, the underlying message is similar. At the Planck scale, space-time is not smooth, not static, and not passive. It is active, fluctuating, and deeply intertwined with quantum processes. This raises an important question. If space-time is so restless at small scales, why does it appear so stable at larger ones? Why does the foam not leak into everyday physics? The answer likely lies in averaging and suppression. Quantum fluctuations are most significant when the relevant scales are comparable to the Planck length. At larger scales, fluctuations average out. Random variations cancel. Only coherent long wavelength features remain. This is analogous to noise in many systems. At small scales, noise dominates. At large scales, signal emerges. The smooth geometry of space-time may be the signal, emerging from the noise of quantum foam. There may also be mechanisms that actively suppress large-scale fluctuations. Interactions among underlying degrees of freedom could favor stable configurations, much like interactions among atoms favor certain phases of matter. Space-time may settle into a low-energy state that is smooth and classical. If this is the case, then quantum foam is not something that exists everywhere in the same way. It is a description of space-time behavior at very high energies or very small scales. Under ordinary conditions, space-time is far from that regime. However, there are places where the foam may become relevant again, near black hole horizons where gravity is strong, near the beginning of the universe where densities and energies were extreme. In these environments, Planck-scale physics may leave observable traces. This possibility motivates much of modern research. Physicists look for subtle signatures of Planck-scale fluctuations in cosmological data, gravitational waves, or high-energy astrophysical phenomena. So far, no definitive evidence has been found, but the search continues. There is also a conceptual payoff, even without experimental confirmation. The idea of quantum foam forces us to rethink what space is. It suggests that emptiness is not inert. Even when nothing else is present, space itself has structure and dynamics. This challenges the intuitive idea of vacuum as nothingness. In modern physics, vacuum is the lowest energy state of a system, not the absence of a system. Quantum foam pushes this further. Even the vacuum of space-time may be restless. At the same time, it is important to avoid overstating the case. Quantum foam is not proven. It is a way of organizing our ignorance. It reflects what happens when we extrapolate known theories into an unknown regime. Future theories may replace foam with something more precise. They may show that the foam picture is misleading in important ways. What is likely to remain is the conclusion that space-time at the smaller scales is not smooth and not static. As we sit with this idea, it becomes clear that restless space is not an obstacle to understanding. It is an invitation to expand our conceptual toolkit. It suggests that geometry is not the starting point, but the outcome. For most of our lives, gravity feels like the quietest force in the room. It keeps your feet on the floor, holds the moon in orbit, and gently guides planets around stars, but it rarely announces itself dramatically. You don't feel gravity switching on or off. You don't notice it changing from moment to moment. Compared to electricity, magnetism, or even friction, gravity feels subtle, almost shy. It works patiently in the background, shaping the large-scale structure of the universe without much fuss. In physics, this impression is backed up by numbers. Gravity is extraordinarily weak compared to the other fundamental interactions. The electromagnetic force between two electrons is roughly 40 orders of magnitude stronger than their gravitational attraction. That difference is so vast it's hard to picture. If gravity were even slightly stronger, stars would burn out quickly, planets would collapse, and the universe would look nothing like it does. If it were much weaker, galaxies might never form at all. Gravity's weakness is part of what makes the universe stable and long-lived. Because of this, it feels counterintuitive to hear physicists say that gravity becomes unusually loud at tiny scales. Loud here does not mean audible, of course. It means dominant, unavoidable, impossible to ignore. The same force that barely nudges particles toward one another at everyday scales becomes the central player when we push our descriptions of reality down toward the Planck scale. To understand why, we need to step away from everyday intuition and look carefully at how gravity works in modern physics. Gravity is not just another force acting within space. In Einstein's description, gravity is the behavior of space-time itself. Mass and energy curve space-time, and that curvature dictates how objects move. Gravity is geometry in action. At large scales, this geometry changes gently. The curvature produced by a planet or even a star spreads out over vast distances. The resulting gravitational field is smooth and predictable. Small objects moving through this field follow well-defined paths. The geometry feels stable. At small scales, especially when energy densities become extreme, this calm picture breaks down. The key quantity here is not mass alone, but energy density. Gravity responds to how much energy is packed into a given region of space-time. You can have a small amount of total energy that produces negligible gravity if it is spread out. The same amount of energy concentrated into an extremely tiny region can produce intense gravitational effects. This is where scale matters. As we consider smaller and smaller regions of space, the same amount of energy corresponds to a higher and higher energy density. At ordinary scales, quantum fluctuations in energy are tiny compared to the size of the region, so their gravitational effects are negligible. As the region shrinks, those same fluctuations become increasingly significant. Quantum mechanics tells us that energy cannot be perfectly smooth or constant. Even in vacuum, energy fluctuates. These fluctuations are usually averaged out and unnoticeable, but gravity does not care whether energy is steady or fluctuating. Any energy contributes to curvature. As we approach the Planck scale, the typical size of quantum energy fluctuations becomes comparable to the energy required to significantly curve space-time. At that point, gravity stops being ignorable. It becomes the loudest influence in the system. This is one reason gravity dominates at tiny scales, even though it is weak in everyday situations. Weakness is not absolute. It depends on scale. Gravity's influence grows with energy density, not with distance alone. Another way to see this is through dimensional analysis. The Planck scale is defined by combining the gravitational constant with the constants of quantum mechanics and relativity. This combination tells us that at a certain energy scale, gravitational interactions become as strong as quantum interactions. That scale corresponds to extremely small distances. Below that scale, the separation between gravitational physics and quantum physics disappears. You can no longer treat gravity as a smooth background, and quantum effects as small corrections. Gravity itself must be treated quantum mechanically. This is what makes gravity loud at tiny scales. It is no longer a gentle background influence. It becomes entangled with every attempt to describe what is happening. This loudness shows up most clearly when we think about measurement. To probe very small distances, we need high energies. High energy means strong gravity. At some point, the gravitational effect of the probing energy dominates the experiment. The probe creates significant curvature. It may even create a black hole. This is not an accident. It is a reflection of gravity's unique role. Gravity couples to everything. It does not distinguish between types of energy or charge. Any form of energy contributes. As energy becomes concentrated, gravity inevitably responds. Other forces do not behave this way. Electromagnetic forces can cancel out due to positive and negative charges. Strong and weak forces act only at very short ranges and involve specific charges. Gravity has no such exclusions. It accumulates. At large scales, this accumulation leads to galaxies, stars, and planets. At tiny scales, it leads to dominance. Another factor is that gravity resists localization. Trying to localize energy sharply increases gravitational effects. This is different from other forces, which often become weaker at short distances due to screening or asymptotic freedom. Gravity does the opposite. Concentration amplifies it. This amplification is why gravity becomes central in discussions of the Planck scale. It is not that gravity suddenly changes its nature, it is that the conditions we impose bring gravity to the foreground. There is also a deeper reason gravity becomes loud at small scales, related to the nature of space-time itself. Gravity is not something that happens in space-time. It is what space-time does. When space-time itself becomes subject to quantum uncertainty, gravity cannot remain quiet. Quantum fluctuations in energy imply fluctuations in curvature. At small scales, these fluctuations are not smooth ripples. They are abrupt, irregular, and intense. Space-time becomes restless, as discussed earlier. That restlessness is gravity in its most raw form. In this regime, gravity is not a force you calculate after the fact. It is inseparable from the basic description of reality. Any attempt to describe what exists must account for gravitational effects at the same level as quantum effects. This has profound implications. Many of the tools physicists rely on assume that gravity can be neglected or treated classically. At the Planck scale, those tools fail. The loudness of gravity drowns out approximations that work elsewhere. This is one reason why quantum gravity is so difficult. You cannot build it by taking quantum mechanics and adding gravity as an extra interaction. Gravity changes the stage on which quantum mechanics plays out. The loudness of gravity also shows up in black holes. Black holes are regions where gravity has already become dominant, even at macroscopic scales. Near the event horizon, space-time is strongly curved. Near the center, curvature becomes extreme. At the very center, according to classical general relativity, curvature becomes infinite. This is a sign that the theory has gone beyond its limits. Quantum effects must become important before infinity is reached. That transition is expected to occur at the Planck scale. Inside black holes, gravity is already loud enough to overwhelm other forces. Matter is crushed, time and space behave strangely, and classical descriptions fail. The Planck scale likely marks the regime where gravity's loudness forces a new description. The early universe offers another example. In the earliest moments after the Big Bang, energy densities were enormous. Gravity was not weak or gentle, it dominated the behavior of space-time. Quantum gravity effects were likely crucial in shaping the initial conditions of the universe. As the universe expanded and cooled, energy densities dropped. Gravity quieted down, settling into the background role we're familiar with today. But its early loudness may have left subtle imprints on the structure of the cosmos. This history highlights an important point. Gravity's apparent weakness is not universal. It is a feature of the current, low-energy, large-scale universe. At other times and scales, gravity can be anything but quiet. There is also a conceptual aspect to gravity's loudness. Gravity defines what we mean by distance and time. When gravity fluctuates strongly, the very concepts we use to describe physics become unstable. At small scales, if gravity is loud, space-time geometry fluctuates wildly. Distances stretch and shrink unpredictably. Time intervals lose uniformity. In such a regime, it is not just that gravity affects particles, it affects the meaning of location, duration, and order. This distinguishes gravity from other forces. Electromagnetic interactions can be strong without undermining the concept of space itself. Gravity cannot. Strong gravity means strong geometry. Strong geometry means unstable measurement. This is why gravity is so central to discussions of fundamental limits. It is not merely another interaction. It sets the rules for the arena in which interactions occur. Another way to see gravity's loudness is through the idea of universality. Gravity acts on all forms of energy equally. At small scales, quantum fields fluctuate. Each fluctuation carries energy. Each contributes to curvature. There is no way to isolate a subsystem from gravity. In contrast, you can often isolate systems from other forces. You can shield electromagnetic interactions. You can choose particles that do not participate in the strong interaction. You cannot shield gravity. At tiny scales, this universality becomes overwhelming. Every fluctuation matters. Every attempt to define a system pulls gravity into the story. This universality is part of what makes gravity so difficult to quantize. In quantum field theory, interactions are often treated as occurring on a fixed background. Gravity refuses to stay in the background. It insists on being part of the quantum system. The loudness of gravity also challenges the idea of reductionism. In many areas of physics, understanding the smallest parts helps explain the whole. With gravity, the smallest scales are inseparable from the structure of the whole. Local behavior depends on global geometry. This suggests that at the Planck scale, physics may be less about isolated components and more about holistic relationships. Gravity links everything. As these ideas settle in, it becomes clear that gravity's loudness is not an anomaly. It is a consequence of gravity's role as the geometry of space-time and of the way energy behaves at small scales. The quiet gravity of everyday life is the result of averaging expansion and low energy density. The loud gravity of the Planck scale is what remains when those calming factors are removed. Understanding this shift is essential for understanding what really happens when space reaches the Planck scale. It explains why space-time becomes unstable, why measurement breaks down, and why familiar descriptions fail. The natural question is how gravity's loudness affects order and structure. If gravity dominates and geometry fluctuates, what happens to cause and effect? What happens to direction, sequence, and predictability? In everyday life, cause and effect feel solid and dependable. You flip a switch and the light turns on. You drop a cup and it falls to the floor. Events line up in a clear sequence, one following another, forming a direction that feels unavoidable. The past leads to the present leads to the future, and not the other way around. This sense of order is so ingrained that it feels less like a feature of the universe and more like a basic rule of existence. Physics has long relied on this intuition. Classical mechanics is built on deterministic cause and effect. If you know the forces acting on an object and its initial conditions, you can predict its future motion. Even when quantum mechanics complicated this picture by introducing probabilities, it preserved a clear causal structure. Causes still precede effects. Measurements still occur in time. Outcomes may be uncertain, but the sequence of events remains ordered. As we approach the Planck scale, however, this familiar structure begins to loosen. The breakdown of smooth space-time, the loudness of gravity, and the instability of measurement all contribute to a deeper disruption. It is not just that events become hard to predict. It is that the concepts of cause, order, and direction themselves may stop applying in the way we expect. To see why, it helps to examine what causality depends on. Cause and effect rely on a well-defined notion of time. There must be a before and an after. Events must be ordered along a temporal dimension. There must also be a stable space-time structure that defines which events can influence which others. Signals cannot travel faster than light. Influences propagate locally. These constraints give causality its shape. At large scales, space-time provides this structure reliably. Light cones define what can affect what. Time flows consistently enough that ordering events is straightforward. Even in relativity, where simultaneity is relative, causal order is preserved. All observers agree on which events can influence which others. At the Planck scale, these foundations begin to erode. If space-time geometry fluctuates violently, then the light cones that define causal structure fluctuate as well. The distinction between time-like, space-like, and null separations becomes uncertain. Events may not have a fixed causal relationship. This does not mean that anything can cause anything else in a chaotic free-for-all. It means that the classical notion of a fixed causal order may no longer apply at the deepest level. Causality may still exist, but in a different form. One reason for this breakdown lies in quantum uncertainty. In quantum mechanics, events are not always sharply localized in space and time. A particle does not follow a single trajectory. It exists in a superposition of possibilities. When space-time itself becomes subject to quantum uncertainty, the locations and times of events become fuzzy as well. If you cannot precisely locate an event in time, then saying whether it occurred before or after another event becomes ambiguous. Ordering loses precision. Sequence becomes approximate. Another contributing factor is the role of gravity. As discussed earlier, gravity becomes dominant at tiny scales. Strong gravity warps space-time severely. In extreme cases, such as near black holes, time and space can exchange roles. Inside an event horizon, what was once a spatial direction becomes temporal. The concept of direction itself changes. At the Planck scale, similar but more radical effects may occur. If space-time fluctuates, the distinction between spatial and temporal directions may not be fixed. What counts as forward in time in one moment may not be well defined in the next. This challenges the idea of a universal arrow of time. In thermodynamics, the arrow of time is associated with increasing entropy. At macroscopic scales, entropy increases reliably, giving time a direction. At microscopic scales, the laws of physics are mostly time-symmetric. They do not prefer a direction. At the Planck scale, where space-time itself is unstable, the thermodynamic arrow may not yet exist. Entropy requires a system with many degrees of freedom and a notion of state counting. If space-time and matter are too primitive or too fluctuating, entropy may not be well defined. Without a thermodynamic arrow, time loses its directionality. There may still be change, but not a preferred sequence from past to future. Direction becomes an emergent property, not a fundamental one. This idea can feel unsettling because it undermines a deeply human way of understanding the world. We think in stories. Stories have beginnings, middles, and ends. Causes lead to effects. Removing that structure feels like removing meaning itself. But physics has shown repeatedly that meaning at human scales emerges from rules that look very different at fundamental scales. The absence of a fundamental arrow of time does not mean the absence of experience time. It means that experience time arises from conditions that are not always present. Another way to approach this breakdown is through the concept of locality. In classical physics, causes act locally. An event influences nearby events, which then influence others. This chain relies on stable spatial relationships. If space-time connectivity fluctuates, locality becomes ambiguous. At the Planck scale, two events that appear separate at large scales may be connected through transient structures. Conversely, events that are nearby in an average sense may be temporarily disconnected. This undermines the idea of a fixed causal neighborhood. Quantum entanglement adds another layer. Entangled systems exhibit correlations that do not depend on distance in the usual way. While entanglement does not allow faster-than-light communication, it does challenge classical intuitions about separability. If space-time itself emerges from entanglement patterns, as some theories suggest, then causal structure may also emerge from those patterns. Cause and effect may not be fundamental relations, but emergent ones. In such a picture, fundamental processes are not ordered by time. They are related by constraints and correlations. Time ordering appears when these processes are coarse-grained, averaged over many degrees of freedom. This idea appears in several approaches to quantum gravity. Some formulations describe the universe in terms of states and transitions without a global time parameter. Instead of evolution in time, there are relations between states. Time emerges as a convenient label for sequences of correlated changes. In these frameworks, asking which event caused which may not make sense at the deepest level. What makes sense is asking how events are related and how those relations give rise to an effective causal order at larger scales. This does not mean that causality is an illusion. It means that causality is scale-dependent. At large scales, it is robust and reliable. At small scales, it may dissolve into something more primitive. Directionality faces a similar fate. Direction depends on stable geometry. It requires a notion of orientation. If spacetime geometry fluctuates, orientation may not be well defined. Directions may not persist long enough to matter. This affects not only spatial directions, but temporal ones as well. Forward and backward in time may not be meaningful distinctions at the Planck scale. Instead, there may be change without direction, a kind of unordered dynamism. This unordered behavior does not imply randomness without structure. Quantum mechanics itself is highly structured despite its probabilistic nature. The breakdown of order may be governed by deep principles that we do not yet understand. There is also a connection here to symmetry. Many fundamental laws are symmetric under time reversal. They do not distinguish between past and future. The asymmetry we experience arises from boundary conditions, not from the laws themselves. At the Planck scale, boundary conditions may be very different from those we're used to. The early universe, for example, may have started in a highly ordered state that allowed an arrow of time to emerge. Before that, if such a before makes sense, direction may not have existed. Inside black holes, similar questions arise. Near the centre, where classical descriptions fail, time and space lose their usual meanings. Cause and effect may not follow familiar patterns. Information may not be lost, but its flow may not be describable in temporal terms. These considerations highlight that cause, order, and direction are not absolute features of reality. They are features of a particular regime. They depend on space-time being stable, smooth, and classical. When those conditions fail, our usual narratives fail with them. This does not mean that reality becomes incomprehensible. It means that comprehension requires new concepts. It is tempting to imagine the Planck scale as a chaotic blur where nothing makes sense. That image is misleading. Chaos implies a breakdown of rules. What likely exists instead is a different set of rules, ones that do not prioritize time ordering and causal chains. The challenge is that our minds are tuned to think in terms of sequences. We experience the world as a flow. Translating a timeless or orderless description into human language is inherently difficult. Yet physics has managed similar translations before. Wave-particle duality, superposition, curved space-time all required abandoning intuitive pictures. The breakdown of cause and order at the Planck scale may require a similar leap. Importantly, the breakdown is not total, it is contextual. At scales much larger than the Planck length, space-time settles into a configuration where order re-emerges. Causal chains become reliable, direction becomes meaningful, the world becomes navigable. Understanding how this transition occurs is one of the central goals of quantum gravity research. How does a world without fixed order give rise to a world with arrows of time and chains of cause and effect? Some ideas suggest that decoherence plays a role. As systems interact and entangle with their environment, certain histories become more stable. Order emerges through interaction. Direction emerges through accumulation. Others suggest that space-time itself undergoes a phase transition. At high energies, it behaves in one way. At lower energies, it condenses into a smooth geometry with causal structure. These ideas remain speculative, but they point toward a consistent picture. The breakdown of cause and order at tiny scales is not a flaw, it is part of the foundation from which the ordered world arises. When we imagine breaking something down to its most basic form, we often reach for familiar metaphors. Matter is made of atoms, images are made of pixels, music is stored as digital samples. In each case, continuity turns out to be an illusion created by resolution. Zoom in far enough, and the smooth surface reveals its discrete structure. It's natural then to ask whether space itself follows the same pattern. If there is a smallest meaningful length, does that mean space is made of tiny pieces like pixels on a screen, stitched together to form the world we experience? This question sits at the heart of many modern debates about the nature of space-time. It is not a simple technical issue. It is a question about what kind of thing space is. Is it fundamentally discrete, built from countable units that exist independently of observation? Or is it something more fluid, something that emerges from relationships, probabilities, and interactions without having a fixed underlying grid? The pixel metaphor is tempting because it aligns with our technological intuition. Digital systems have limits of resolution. Below a certain scale, information is no longer continuous. A pixel is not a smaller version of an image. It is a basic unit that only gains meaning when arranged with others. If space were like this, then the Planck length might represent the size of a fundamental pixel of reality. Some approaches to quantum gravity seem to support this idea. In certain models, areas and volumes take on discrete values. There is a smallest possible area, a smallest possible volume. Geometry becomes quantized. Instead of smooth curves, space-time is described in terms of combinatorial structures, networks, or graphs. Distances arise from how these elements are connected. In such pictures, space is not infinitely divisible. You cannot keep cutting it in half forever. Below a certain scale, there is nothing smaller to cut. The pixel idea, in a loose sense, applies. There are basic units, and everything larger is built from them. But this picture has limits. Pixels on a screen exist in space. They have positions relative to one another. They are laid out on a grid. If space itself were made of pixels in this straightforward way, we would still need a space in which those pixels exist. That leads to an infinite regress. Space would be made of things that exist in space. To avoid this, many theories propose that the fundamental units are not located in space at all. Instead, they give rise to space through their relationships. The basic elements may be abstract, mathematical, or informational. Space emerges as a way of describing how these elements are connected. In this view, space is not made of pixels in the usual sense. It is made of possibilities, relations, and interactions. The Planck scale does not mark the size of a tiny tile. It marks the scale at which spatial description gives way to relational description. This shift is subtle but profound. A pixel is a thing. A possibility is not. A pixel exists whether or not it is used to display an image. A possibility exists only in relation to something else. It is defined by what could happen, not by what already is. Quantum mechanics is built on possibilities. Particles do not have definite positions until they are measured. They exist in superpositions of potential outcomes. The act of measurement selects one outcome from many. This does not mean the others were unreal. They were part of the structure of the system. If space-time itself is quantum, then it may also be built from possibilities rather than fixed elements. At the smallest scales, geometry may not be definite. Distances may exist only as probabilities. Connections may be potential rather than actual. In such a picture, asking whether space is discrete or continuous may be the wrong question. It may be neither, in the classical sense. It may be something that only looks discrete or continuous when viewed from the right perspective. Consider how a wave function behaves. It is continuous, but measurement outcomes are discrete. The underlying description is smooth, but what we observe comes in jumps. Space may behave similarly. The underlying structure may not be a grid, but measurements of geometry may yield discrete results. This duality complicates the pixel metaphor. Pixels are discrete at the fundamental level. Possibilities are not discrete objects. They are descriptions of what could be. If space is made of possibilities, then its apparent discreteness may be an emergent feature of how those possibilities are resolved. Another approach suggests that space-time emerges from quantum entanglement. Entanglement describes correlations between parts of a system that cannot be explained by classical separation. In some theoretical frameworks, the pattern of entanglement between quantum degrees of freedom determines the geometry of space. In these models, distance is not fundamental. It is a measure of how strongly different parts of the system are entangled. Strongly entangled regions appear close together. Weakly entangled regions appear far apart. Space is not something that exists independently. It is a map of relationships. From this perspective, space is not made of pixels because there are no pre-existing units laid out in a grid. There are only quantum degrees of freedom and their correlations. Geometry emerges as a convenient way of summarizing those correlations at large scales. This idea has a striking implication. If space is made of possibilities and relationships, then it is not static. It can change as relationships change. Geometry becomes dynamic at a deeper level than general relativity suggests. Not just curved, but emergent. This aligns with the idea that space-time at the Planck scale is restless. If the underlying possibilities are constantly fluctuating, then the emergent geometry will fluctuate as well. Smoothness appears only when fluctuations average out. The pixel picture, by contrast, suggests a fixed underlying lattice. Even if geometry fluctuates, the lattice remains. Many physicists are skeptical of this because a fixed lattice would single out preferred directions and scales, breaking symmetries that are central to modern physics. Lorentz symmetry, for example, states that the laws of physics are the same for all observers moving at constant velocity. A fixed space-time lattice would likely violate this symmetry. A relational or possibility-based structure has a better chance of preserving it. This is not to say that discreteness is ruled out. Some discrete structures can preserve symmetries in subtle ways, but it shows that the pixel metaphor must be handled with care. Another issue is how time fits into the picture. If space is made of pixels, what about time? Is time also pixelated? Does it advance in discrete steps? Some theories suggest that time may also have a smallest unit. Others suggest that time is emergent in a different way than space. If both space and time are made of discrete units, then reality would resemble a digital simulation. This idea has gained popularity in some philosophical circles, but physics does not require such a literal interpretation. Discreteness in a measurement does not imply discreteness in ontology. Quantum mechanics already shows us that nature can be probabilistic without being digital in a simple sense. Outcomes are discrete, but underlying dynamics are continuous. Space may follow a similar pattern. The possibility-based view also helps make sense of why measurement breaks down at the Planck scale. If geometry is not definite until it is measured, then trying to measure it with extreme precision forces a resolution of possibilities that cannot be sustained. The act of measurement overwhelms the system. In this sense, the Planck length marks the scale at which spatial possibilities become too numerous or too unstable to resolve into a single outcome. Space does not stop existing, it stops being definite. This also connects to the earlier discussion of causality. If space is made of possibilities, then causal order may also be potential rather than fixed. Events may not have a single sequence until coarse-grained. This picture is difficult to visualize, and that is not an accident. Human intuition evolved to navigate a world where space and time are stable. We are not equipped to imagine a reality where geometry itself is probabilistic. Yet mathematics allows us to describe such possibilities, and physics has repeatedly shown that intuition is not a reliable guide at fundamental scales. The question of pixels versus possibilities also influences how physicists search for a theory of quantum gravity. If space is made of pixels, then the goal is to identify the fundamental building blocks and the rules by which they connect. If space is made of possibilities, then the goal is to understand the underlying quantum structure from which geometry emerges. These approaches are not mutually exclusive. It may be that there are discrete elements, but their significance lies not in their individual existence, but in the space of possibilities they generate. The basic units may not be geometric at all. Geometry may be a secondary description. What matters for the present discussion is that the Planck scale does not force a simple answer. It does not tell us that space is a grid or that it is infinitely divisible. It tells us that our usual categories fail. The pixel metaphor captures the idea of a smaller scale. The possibility metaphor captures the idea of indeterminacy and emergence. Reality at the Planck scale may involve aspects of both, without fitting neatly into either. As we reflect on this, it becomes clear that asking what space is made of may be less important than asking how space behaves. Does it behave as something fixed, or something dynamic? Does it exist independently or relationally? Does it have properties before measurement or only in interaction? Time feels unavoidable. It is the backdrop of every thought, every memory, every expectation. You wake up, the day unfolds, night arrives, and eventually sleep pulls you forward again. Even when nothing seems to be happening, time is still there, quietly passing. We are so accustomed to this presence that imagining a reality without time feels almost impossible. And yet, as physics approaches the Planck scale, that is exactly what it is forced to consider. At familiar scales, time behaves well. Clocks tick, causes precede effects, durations can be measured and compared. Even when relativity complicates matters by making time flow at different rates, for different observers, time itself remains a meaningful quantity. There is still a before and an after, even if different observers disagree on the details. Time, though flexible, remains real. Quantum mechanics, despite all its strangeness, does not remove time either. In standard formulations, time is treated as an external parameter. Systems evolve in time. Probabilities change with time. Measurements occur at specific moments. Quantum theory assumes time rather than explaining it. This comfortable arrangement begins to unravel when gravity enters the quantum picture. General relativity tells us that time is part of space-time, shaped by mass and energy. Quantum mechanics tells us that energy fluctuates. When space-time itself becomes subject to quantum fluctuations, time can no longer be treated as a stable backdrop. It becomes part of the system, not a container around it. At the Planck scale, this tension reaches a breaking point. The equations that attempt to describe the universe as a whole, including gravity and quantum mechanics, often do something remarkable. They lose time altogether. One of the most famous examples is the Wheeler-DeWitt equation, which arises in certain approaches to quantum gravity. Unlike the Schrödinger equation, which explicitly includes time, this equation does not contain a time variable at all. It describes the quantum state of the universe as a whole, but it does so without reference to time passing. This is not a mathematical oversight. It is a reflection of a deep problem. If the universe contains everything, there is no external clock to measure its evolution against. Time cannot be something outside the universe if the universe is all there is. This leads to a startling possibility. At the deepest level, time may not exist in the way we think it does. It may not flow. It may not tick. It may not even be a fundamental feature of reality. This does not mean that change disappears. Things still happen. Configurations differ. States are not all the same. What disappears is the idea that these differences are ordered along a single, universal temporal dimension. To understand how radical this is, consider what we usually mean by before. Before implies an ordering. Event A happens, then event B happens. Even if the events are probabilistic, even if their timing is uncertain, there is still an assumption that one precedes the other. At the Planck scale, that assumption may fail. Events may not be ordered in time in any fundamental way. They may simply coexist as possibilities or relations within a larger structure. This is why physicists sometimes talk about a regime where before does not exist. Not metaphorically, but literally. There may be no meaningful sense in which one can say that one configuration came earlier than another. This idea challenges not just physics but language itself. Our grammar is built around time. Verbs have tenses. Narratives have sequences. Asking us to think without time is like asking us to think without space, and yet, physics keeps pointing in this direction. One way to approach this is through the idea that time is emergent. Just as temperature emerges from the collective motion of particles, time may emerge from the collective behavior of more fundamental degrees of freedom. At large scales, where many degrees of freedom interact and stabilize, time appears as a reliable ordering parameter. At small scales, where fluctuations dominate and no stable background exists, time may not yet have emerged. This perspective helps reconcile the apparent timelessness of fundamental equations with the undeniable experience of time. Time is not fundamental, but it is real in the regime we inhabit. Near the Planck scale, however, the conditions required for time to emerge may not be present. Geometry fluctuates, causality blurs, measurement fails. Without stable sequences of events, time has nothing to anchor itself to. Another way to think about this is through relational time. In some approaches, time is not something that exists on its own. It is a way of describing change relative to something else. One system changes compared to another. One configuration is correlated with another. In this view, time is not a thing, but a comparison. If nothing changes, there is no time. If everything changes but without stable correlations, there may still be no time in a meaningful sense. At the Planck scale, changes may be too rapid, too chaotic, or too unstructured to support stable comparisons. Without stable reference processes, there is nothing to function as a clock. Clocks themselves are physical systems. They rely on regularity. A pendulum swings, an atom oscillates, a crystal vibrates. All of these processes assume a stable space-time background. At the Planck scale, that background may not exist. If space-time geometry fluctuates violently, any process that could serve as a clock would be disrupted. Regularity would be impossible. Without regularity, duration loses meaning. This leads to the idea that time near the Planck scale is not just short or distorted. It is undefined. Not hidden, not compressed, but conceptually absent. This absence does not imply a void. It implies a different mode of existence. Instead of a timeline, there may be a landscape of possible states. Instead of evolution, there may be relations among states. Some physicists describe this using the metaphor of a block universe, where past, present, and future all coexist. Others go further, suggesting that even that picture relies too heavily on temporal intuition. In more radical views, the universe is described as a collection of nows, complete configurations that do not evolve. The experience of time arises because these configurations contain records, memories, and correlations that create the illusion of sequence. In such a framework, what we call the past is encoded in the present through memory. What we call the future is a set of possibilities inferred from the present. Time is not something flowing, it is something inferred. Near the Planck scale, such inference may not be possible. Configurations may not contain records. There may be no memory structures. Without memory, there is no past. Without anticipation, there is no future. There is only configuration. This idea helps explain why the early universe is so difficult to describe. If time did not exist in a meaningful way at the very beginning, then asking what happened before the Big Bang may be meaningless. There was no before. This is not a claim about ignorance, it is a claim about language. Before presupposes time. If time is emergent, then there is no temporal dimension prior to its emergence. The same reasoning may apply to black holes. Inside a black hole, space-time behaves in extreme ways. Classical descriptions suggest that time and space exchange roles. At the Planck scale, near the core, even that description likely fails. Time may cease to be meaningful in any conventional sense. This does not mean that black holes erase reality. It means that reality inside them may not be ordered temporally in the way we expect. Another clue comes from entropy. The arrow of time we experience is closely tied to increasing entropy. Entropy requires a notion of state counting and coarse graining. At the Planck scale, where states may not be well defined in space-time terms, entropy may not exist. Without entropy, there is no thermodynamic arrow. Without an arrow, time loses direction. Without direction, before and after blur together. This suggests that the arrow of time emerges along with space-time itself. As the universe expands and cools, degrees of freedom organize. Entropy begins to increase. Time gains direction. Near the Planck scale, before this organization occurs, time has not yet taken shape. It is important to emphasize that this does not contradict experience. We do not live at the Planck scale. We live in a regime where space-time is stable, entropy increases, and time flows reliably. The absence of time at the deepest level does not negate the presence of time at our level. Physics has encountered similar situations before. Atoms do not have temperature, yet temperature is real. Individual molecules do not have pressure, yet pressure is real. The absence of time at the fundamental level does not make time an illusion, it makes it emergent. This perspective also helps explain why time is treated differently in different theories. In quantum mechanics, time is external because the theory applies to systems within space-time. In general relativity, time is part of the system because space-time itself is dynamic. In quantum gravity, time may disappear because there is no longer a separation between system and background. The Planck scale is where this disappearance becomes unavoidable. As we move closer to this boundary, it becomes clear that time is not just stretched or slowed, it is transformed. It stops being a universal parameter and becomes something that only makes sense under certain conditions. This transformation does not happen abruptly. It happens gradually, as the assumptions required for time weaken. Measurement becomes unreliable, geometry fluctuates, causality blurs. Eventually, time has nothing left to attach itself to. From here, the discussion naturally shifts toward how such a timeless regime could give rise to the temporal world we know. How does time emerge? How does order form? How does direction appear? These questions do not have final answers yet. They remain open, but they point toward an understanding of the universe where time is not the starting point, but the outcome. And as strange as that may sound, it fits a broader pattern in physics. The most familiar features of reality often turn out to be the least fundamental. They arise not because they are basic, but because they are stable. Time near the Planck scale may not exist as we know it. But from that absence, through processes we are only beginning to glimpse, the steady flow of moments we live within quietly takes shape, setting the conditions for clocks, memories, and stories to exist at all. Black holes have always occupied a strange position in physics. They are predicted by equations that work extraordinarily well, yet they represent situations where those same equations reach their breaking point. They are not hypothetical curiosities anymore. We observe their effects on stars, on gas, on entire galaxies. We detect the ripples they send through space-time when they collide. And still, when we look closely, black holes remain places where our understanding of reality becomes uncertain. At first glance, black holes seem like purely gravitational objects, regions where gravity has become so strong that nothing, not even light, can escape. But this description hides something deeper. Black holes are not just strong gravity. They are places where gravity, space, time, and quantum effects are forced into direct confrontation. They are among the few natural settings where Planck-scale physics may leave observable traces. To see why, it helps to step through what a black hole actually is in the language of general relativity. A black hole forms when matter is compressed into a region so dense that space-time curves inward on itself. The event horizon marks the boundary beyond which escape is impossible. Outside the horizon, space-time behaves in extreme but predictable ways. Inside, classical theory predicts a singularity, a point where curvature becomes infinite and physical quantities lose meaning. Physicists do not take this infinity literally. Infinite curvature is a sign that the theory has been pushed beyond its domain. The singularity is not necessarily a real object. It is a placeholder for physics we do not yet understand. Most physicists believe that quantum gravity effects become important before the singularity is reached, replacing it with something finite but unfamiliar. This belief alone makes black holes relevant to Planck physics. The densities and curvatures near the core of a black hole approach the Planck scale. Whatever replaces the classical singularity must be governed by the same physics that applies when space reaches its smallest, meaningful structure. But the whisper of Planck physics does not come only from the core. It comes from the horizon as well. For a long time, black holes were thought to be completely black. Nothing escapes. Nothing leaks out. Then Stephen Hawking showed that this picture changes when quantum mechanics is taken into account. Black holes emit radiation, very slowly, very faintly, but inevitably. This Hawking radiation arises from quantum effects near the event horizon. The details are subtle, but the implication is profound. Black holes are not isolated from the quantum world. Quantum fluctuations at the horizon can produce real particles that escape to infinity. Over immense timescales, a black hole can lose mass and eventually evaporate. This immediately raises a question that cuts straight to the heart of Planck-scale physics. What happens to the information that fell into the black hole? In quantum mechanics, information is not supposed to be destroyed. The evolution of quantum systems is reversible in principle. Hawking's original calculation suggested that black hole evaporation is purely thermal, carrying no information about what fell in. If that were true, information would be lost forever, violating a core principle of quantum theory. This tension is known as the black hole information problem. It has driven decades of research and debate. It is not a technical puzzle about bookkeeping. It is a clash between two pillars of modern physics. Resolving this problem requires understanding how quantum information behaves in a regime where space-time is strongly curved and possibly fluctuating at the Planck scale. Black holes are not just objects in space-time. They test the consistency of space-time itself. One of the most striking lessons from black hole physics is that geometry and information may be deeply connected. The amount of information a black hole can contain is not proportional to its volume, as one might expect. It is proportional to the area of its event horizon. This result, known as the Bekenstein-Hawking entropy, suggests that the fundamental degrees of freedom of a black hole scale with surface area, not bulk. This is wildly counterintuitive. It implies that the information content of a region of space may be encoded on its boundary. This idea has enormous implications. It suggests that space-time itself may be holographic, meaning that a lower dimensional description on a boundary fully captures the physics of a higher dimensional region. In such a picture, space is not fundamental. It emerges from more basic, lower dimensional degrees of freedom. The holographic principle did not come from abstract speculation. It was forced upon physicists by black holes. Black holes whispered that something was wrong with our intuition about space, volume, and information. If the deepest description of reality is holographic, then Planck-scale physics is not just about tiny distances. It is about how information is organized. Geometry may be secondary, a way of packaging information rather than a fundamental stage. This idea aligns with earlier discussions about space being made of possibilities rather than pixels. In a holographic framework, there is no tiny grid filling space. There are degrees of freedom living on boundaries, entangled in ways that give rise to the illusion of volume. Black holes also challenge our understanding of time. From the perspective of a distant observer, an object falling toward a black hole never quite reaches the event horizon. Its clock appears to slow down, freezing in time as it approaches. From the perspective of the falling object, nothing special happens at the horizon. It crosses smoothly and continues inward. These two perspectives are both correct, and they cannot be combined into a single classical picture. This tension hints that space-time description is observer-dependent in a deep way, especially near horizons. At the Planck scale, such observer dependence may become unavoidable. There may be no single, global description of space-time that all observers agree on. Instead, reality may be stitched together from complementary perspectives, each valid in its own domain. This idea is sometimes called black hole complementarity. It suggests that what happens inside a black hole and what happens outside are not contradictory, but they cannot be described simultaneously in a single classical framework. Complementarity hints that space-time at the Planck scale is not a single, objective structure. It may depend on how information is accessed and by whom. Geometry becomes relational, tied to observation and interaction. Another whisper from black holes comes from their thermodynamic behavior. Black holes have temperature, they have entropy, they obey laws that closely resemble the laws of thermodynamics. This is remarkable because thermodynamics is usually associated with systems made of many microscopic constituents. A gas has temperature because its molecules move. A solid has entropy because its atoms can arrange themselves in many ways. If black holes have thermodynamic properties, then they must have microscopic degrees of freedom. These degrees of freedom are not described by classical space-time geometry. They must belong to a deeper level of description, likely governed by Planck-scale physics. In this sense, black holes act like macroscopic probes of microscopic space-time structure. Their large-scale behavior reflects the collective behavior of fundamental degrees of freedom we do not yet fully understand. This perspective turns black holes into laboratories. We cannot experiment with them directly, but their theoretical properties constrain what a theory of quantum gravity can look like. Any viable theory must explain black hole entropy, Hawking radiation, and information preservation. These constraints are powerful. They have ruled out entire classes of speculative models. They have guided the development of string theory, loop quantum gravity, and holographic dualities. Another lesson from black holes concerns the nature of singularities. Classical general relativity predicts singularities, but quantum gravity is expected to smooth them out. Various models propose different resolutions. Some replace the singularity with a dense core. Others suggest a bounce. Others propose that space-time ends in a more subtle way. While these details remain uncertain, the common theme is that Planck-scale physics intervenes to prevent infinite curvature. Black holes tell us that space-time cannot be infinitely compressed. There is a limit, and beyond it, new physics appears. This reinforces the idea of a smallest meaningful length. The Planck scale acts as a regulator, preventing geometry from collapsing into meaningless infinities. Black holes also blur the line between inside and outside. The event horizon is not a physical wall, it is a causal boundary. Yet it plays a crucial role in encoding information and defining entropy. This suggests that boundaries are fundamental. The distinction between regions of space may not be primary. What matters may be how regions are separated by causal structure. At the Planck scale, causal boundaries may fluctuate. Horizons may form and dissolve. The clean separation between inside and outside may break down. Black holes offer a glimpse of this behaviour in an extreme but controlled setting. There is also a deep connection between black holes and the early universe. Both involve extreme densities and curvatures. Both may involve horizons. Both challenge our understanding of time and causality. Some physicists suspect that the Big Bang itself may be described in terms similar to a black hole, but run in reverse. If so, insights from black hole physics may apply to cosmology as well. Black holes, in this sense, are not isolated oddities. They are windows. They allow Planck-scale physics to influence macroscopic phenomena in ways we can study indirectly. It is important to note that black holes do not shout their secrets. They whisper. The signals are subtle. Hawking radiation is extremely faint. Information recovery, if it occurs, is spread over enormous timescales. Observational access is limited. But in theoretical physics, whispers can be enough. A small inconsistency can point to a deep truth. Black holes have repeatedly done this. They have exposed tensions between our best theories and forced us to rethink basic assumptions. They suggest that space is not fundamental, that time may be emergent, that information is more basic than geometry, that boundaries matter more than volumes. None of these conclusions are final. They are hints, not answers. But they are consistent hints, pointing toward a picture where Planck-scale physics governs the deeper structure of reality. As we take these whispers seriously, the role of black holes shifts. They are no longer just cosmic traps or endpoints of stellar evolution. They are messengers from a regime we cannot directly access. They tell us that space-time is not an unbreakable fabric. It can tear, reform, and reorganize at the smaller scales. They tell us that information and geometry are intertwined in ways we're only beginning to understand. When physicists talk about peeking beyond the edge, they are not imagining a literal boundary in space that one could cross. The edge, in this context, is conceptual. It is the point where established theories stop giving reliable answers. It is where equations that have worked flawlessly for decades begin to contradict each other, or return infinities instead of predictions. The Planck scale sits precisely at this edge, and the theories that try to look beyond it are attempts to describe a regime where space, time, gravity, and quantum mechanics no longer behave independently. What all of these theories share is a recognition that something fundamental must change. You cannot simply take the equations of general relativity and apply them unchanged at arbitrarily small scales. You cannot simply extend quantum field theory and expect space-time to remain a passive background. Peeking beyond the edge requires rethinking assumptions that were once considered untouchable. One of the earliest realizations was that gravity resists being treated like other forces. Electromagnetism, the weak force, and the strong force can all be described using quantum field theory on a fixed space-time background. Gravity cannot. When physicists try to quantize gravity using the same methods, the mathematics quickly falls apart. Calculations produce infinite results that cannot be renormalized away. This failure is not a minor inconvenience. It is a signal that the framework itself is wrong for this regime. Theories that peek beyond the edge begin by accepting this signal, rather than trying to ignore it. One broad strategy is to keep space-time continuous, but change its quantum behavior. Another is to abandon continuous spacetime altogether and replace it with something more fundamental. A third is to suggest that spacetime is not fundamental at all, but emergent from deeper structures. String theory is one of the most widely known attempts to go beyond the edge. It begins with a simple but radical idea. The fundamental constituents of reality are not point particles, but one-dimensional objects called strings. These strings can vibrate in different ways, and each vibration mode corresponds to a different particle. This shift from points to extended objects has an important consequence. Point particles can probe arbitrarily small distances, leading to infinities. Strings cannot. Their finite size limits how finely space-time can be probed. When strings interact, they smear out interactions over a small region instead of concentrating them at a point. This softening of interactions helps tame the infinities that plague quantum gravity. In string theory, the Planck length emerges as the scale at which stringy effects become important. Below that scale, the notion of a point loses meaning. Geometry becomes fuzzy, not because of measurement limits alone, but because the fundamental objects do not allow sharp localization. String theory also introduces extra dimensions. These dimensions are not large and extended like the familiar 3 dimensions of space. They are compact, curled up at extremely small scales. The geometry of these extra dimensions influences the properties of particles and forces we observe. While this idea may sound speculative, it arises naturally from the mathematics. Consistency conditions require extra dimensions. Removing them breaks the theory. One of the most intriguing aspects of string theory is its connection to the holographic principle. In certain formulations, a theory of gravity in a higher dimensional spacetime is equivalent to a quantum theory, without gravity on a lower dimensional boundary. This duality suggests that spacetime geometry is not fundamental, but encoded in quantum degrees of freedom living on a boundary. This supports the idea that space is made of possibilities rather than pixels. Geometry becomes a derived concept, emerging from entanglement and information. However, string theory has limitations. It makes predictions at energy scales far beyond current experimental reach. It allows a vast number of possible solutions, known as the landscape, making it difficult to extract unique predictions. Critics argue that it has become too flexible, able to accommodate almost any outcome. Another major approach is loop quantum gravity. Unlike string theory, loop quantum gravity does not introduce extra dimensions or require unification with other forces. It focuses directly on quantizing spacetime geometry itself. In loop quantum gravity, space is described in terms of discrete structures called spin networks. These networks are graphs whose edges and nodes carry quantum numbers that correspond to areas and volumes. Geometry is quantized. There is a smallest possible area and a smallest possible volume. In this picture, space is not smooth. It is made of relational structures. The Planck length sets the scale of these structures. Below that scale, the notion of distance loses meaning because there are no smaller geometric units. Time in loop quantum gravity is treated differently as well. Rather than being a fundamental parameter, time emerges from the evolution of these networks. In some formulations, the universe does not evolve in time at all. Instead, there are relations between configurations. Loop quantum gravity has had some success in resolving classical singularities. In simplified models, the Big Bang singularity is replaced by a bounce. The universe contracts, reaches a minimum size, and then expands again. This suggests that Planck-scale physics can smooth out infinities. Despite these successes, loop quantum gravity also faces challenges. Connecting the theory to observable physics is difficult. Recovering smooth spacetime at large scales is non-trivial. The theory is mathematically complex and still incomplete. Another class of ideas abandon spacetime as a starting point entirely. These approaches suggest that spacetime emerges from more fundamental non-geometric entities. One example is causal set theory. In this framework, the fundamental structure of reality is a set of events with causal relationships between them. There is no space or time as we usually understand them. There is only order. Space and time emerge when these causal relations are coarse-grained. In causal set theory, discreteness is built in from the start. The Planck scale sets the density of events. Geometry arises statistically, not deterministically. Another example involves approaches based on quantum information. These suggest that space-time geometry emerges from patterns of entanglement. The strength and structure of entanglement determine distances and curvature. In these models, space-time is not made of pixels or points. It is made of correlations. Geometry is a way of summarizing how information is shared across a system. This view has gained traction because it offers a way to unify gravity with quantum mechanics conceptually. Quantum mechanics is fundamentally about information and probabilities. If space-time emerges from information, then gravity becomes a property of information flow rather than a fundamental force. There are also approaches that modify gravity itself. Some propose that general relativity is incomplete at small scales and must be altered. These modifications aim to soften singularities or incorporate quantum effects directly into the equations. Such approaches often introduce new fields or change how space-time responds to energy at high densities. While they can resolve certain problems, they risk conflicting with the precise experimental confirmations of general relativity at large scales. Another direction involves asymptotic safety. This idea suggests that gravity may be well defined as a quantum theory after all, not by changing its nature, but by finding a special fixed point in its behavior at high energies. If such a fixed point exists, gravity could remain predictive at all scales. This approach does not rely on new dimensions or discrete space-time. It keeps space-time continuous, but changes how gravity behaves as energy increases. Whether this idea works remains an open question. What unites all these theories is not agreement, but motivation. They are driven by the same failures of existing frameworks. They are attempts to describe a regime where space-time is no longer smooth, where measurement breaks down, where gravity becomes dominant, and where time may not exist as a fundamental parameter. Each theory makes different assumptions about what to keep and what to discard. Some keep geometry, but quantize it. Some keep quantum mechanics, but abandon space-time. Some try to unify everything into a single framework. None of them are complete. None of them are experimentally confirmed. This is not a weakness unique to quantum gravity. It reflects the extreme difficulty of the problem. Peaking beyond the edge means working without direct experimental guidance. It means relying on mathematical consistency, conceptual coherence, and indirect clues from black holes and cosmology. This situation can feel unsatisfying, but it is also historically familiar. At the beginning of quantum mechanics, experimental data outpaced theory. At the beginning of relativity, theory outpaced experiment. In both cases, patience and persistence paid off. Theories that peak beyond the edge may eventually converge. It is possible that string theory, loop quantum gravity, and information-based approaches are different perspectives on the same underlying structure. Or it may be that entirely new ideas are needed. What seems increasingly clear is that space-time is not fundamental in the way we once thought. Whether it's replaced by strings, networks, causal relations, or information, the smooth fabric of space-time appears to be an emergent description. The Planck scale is not just a small length, it is a signpost. It tells us where to stop trusting familiar intuitions and start listening to deeper patterns. As these theories continue to develop, they reshape how physicists think about reality. They shift attention away from objects moving in space and time and toward processes, relations, and structures that give rise to space and time. This shift is not complete. Many questions remain unanswered. How does classical space-time emerge reliably? How does time acquire direction? How does gravity appear weak at large scales? How do these theories connect to observable physics? Yet even in their incompleteness, these theories perform an important function. They show that peeking beyond the edge is possible, even if what we see is still blurry. They demonstrate that the breakdown of old frameworks does not signal the end of understanding, but the beginning of a deeper one. There comes a point in any exploration where moving forward no longer means adding more detail, but allowing what has already been seen to settle. The smallest horizon we can imagine is not a destination in space, and it is not a final answer waiting to be uncovered. It is a limit defined by meaning itself. It is the place where our questions stop behaving like questions we know how to ask, and where description becomes quieter, more careful, less insistent on certainty. Throughout this journey we have followed physics as it moved steadily inward, from smooth space to restless geometry, from clear measurement to blurred definition, from ordered time to a regime where before and after lose their grip. Each step did not erase reality. It stripped away assumptions, and what remains at this smallest horizon is not emptiness, but restraint. The Planck scale is often spoken about as a boundary, but it is not a wall. Nothing crashes into it. Nothing shatters against it. Instead, it behaves like a fading line, where familiar tools lose resolution. Much like a distant shoreline seen through fog, it marks where detail gives way to suggestion. Resting here means acknowledging something subtle but important. Physics does not promise access to every layer of reality in the same way. It promises consistency, not omniscience. When the Planck scale appears again and again across independent arguments, across gravity, quantum mechanics, information theory and black hole physics, it does not declare that nothing lies beyond. It declares that whatever lies beyond does not submit to the same descriptions. This is a difficult posture for human thinking. We are inclined toward completion. We want edges to cross, mysteries to open, doors to lead somewhere else. The smallest horizon resists this impulse. It does not invite conquest, it invites pause. At this scale, space is no longer something to move through. Time is no longer something to flow along. Causality is no longer a sequence. These concepts do not vanish dramatically. They thin out. They lose their sharpness. They stop being reliable guides. And yet the universe does not become arbitrary here. The failure is not of reality, but of expectation. Physics remains structured. It remains constrained. It remains intelligible, but only in a different sense. Relationships replace locations. Correlations replace trajectories. Possibilities replace positions. Resting at this horizon means accepting that the deepest description of reality may not be visualizable. Not because it is mystical, but because it is not spatial in the way our minds are trained to imagine. We evolved to navigate surfaces, distances, durations. We did not evolve to picture the conditions under which space and time themselves come into being. This acceptance is not resignation, it is calibration. The same pattern appears elsewhere in science. We do not ask for the temperature of a single molecule. We do not ask for the pressure at a mathematical point. We do not ask for the trajectory of an electron between measurements. We learn it gradually, that certain questions lose meaning outside the conditions that give them structure. The Planck scale is where questions about where and when undergo the same shift. Importantly, this does not diminish the world we experience. The stability of space and time at human scales is not undermined by their emergence, it is explained by it. What is stable is not fundamental. What is fundamental is what allows stability to arise. When we rest at this smallest horizon, we also notice something else. The universe does not seem eager to reveal its deepest layer through brute force. Increasing energy does not sharpen resolution forever. At some point, more energy destroys information instead of revealing it. Black holes form, horizons appear, access is limited. This behaviour suggests that the universe has built-in protections against certain kinds of inquiry, not as a prohibition, but as a redirection. Instead of asking what lies beneath, physics is nudged toward asking how what we see emerges. This is a profound shift in posture. It moves science away from reductionism as a sole guiding principle and toward emergence as an equally fundamental one. Not everything is best understood by cutting it smaller. Some things are best understood by seeing how they stabilise when many parts interact. The smallest horizon reminds us that explanation is not always excavation. Sometimes it is synthesis. It is also worth noticing how quiet this boundary is. There is no dramatic signal announcing the Planck scale in everyday physics, no sudden anomaly, no breakdown in daily experience. The universe does not flicker or pixelate. The horizon makes itself known only through theoretical consistency. This quietness is telling. It suggests that the Planck scale is not a violent edge, but a gentle limit, a place where language becomes less forceful, where statements become conditional, where certainty gives way to coherence. In this sense, resting at the smallest horizon is not an act of stopping, it is an act of holding. Holding what we know without forcing it into forms it cannot take. There is also something deeply human about this position. Much of human understanding progresses not by final answers, but by learning where questions change. Knowing where to stop asking in one way allows asking differently. Physics at the Planck scale is not finished. New mathematics may arise. New experimental hints may emerge indirectly. New frameworks may unify ideas that currently seem incompatible. None of that is ruled out by this horizon. What is ruled out is the assumption that the universe owes us a picture that fits our intuition. The smallest horizon teaches humility without defeat. It shows that reality is richer than our categories, not poorer. It shows that limits are not failures, but features of coherence. As we rest here, we can also notice that this horizon does not separate us from the universe. It connects us to it. The same physics that governs Planck scale structure governs the stars, the atoms in your body, the signals in your brain. There is no ontological gap, only a descriptive one. What changes across scales is not what exists, but how it can be meaningfully described. And that realization carries a quiet comfort. The universe does not fracture at its deepest level. It reorganizes. It trades geometry for structure, time for relation, motion for correlation. Then, as conditions allow, it builds those familiar concepts back up again. Space returns, time resumes, order stabilizes. Not because they were always there, but because the conditions that support them reappear. Resting at the smallest horizon, then, is not about standing at the edge of nothing. It is about standing at the edge of translation. Beyond this point, reality may still be fully lawful, fully consistent, fully real, but it speaks a language that is no longer spatial or temporal in the way we understand. And there is no urgency to cross that boundary. Physics does not demand that we force meaning where meaning no longer fits. It allows us to recognize where our most trusted ideas do their best work, and where they gracefully step aside. So for now, the smallest horizon remains where we pause. Not because curiosity has ended, but because it has refined itself. Because sometimes the most faithful way to understand the universe is not to push further inward, but to acknowledge the scale at which understanding itself changes shape, and to rest there, quietly, letting the structure of reality remain intact without insisting that it resemble us.